One more. You got lipids, fats, and come on, y'all should have done this in middle school. Sorry, lipids, carbohydrates, and
Simple sugars.
Or carbohydrates. One more.
Is it protein?
Proteins. All right. What are carbohydrates for? What do we mainly use carbohydrates for?
Energy.
In nature, energy. What do we mainly use fats for? What?
It makes it taste sweet.
They do, absolutely. They make things taste good. What else? What do they use for in the body? Huh?
Reserve the energy source.
Nah, there's math. I can't hardly hear y'all. Stored energy. What else?
Water resistant membranes.
Water resistant membranes. What else?
Steroids and hormones.
Steroids and hormones. All right. What about proteins?
Nutrients.
Well, they're all nutrients. So what else?
They're chains of amino acids.
Chains of amino acids.
Regulate cell process.
Regulate cell processes. Do what? Structure. Good. Let's see. Which brings us to ecology, which was where we left off. All right. The biosphere is what?
Every living organism from the deepest ocean turns to the hardest mountain.
About 20 kilometers. What is ecology?
Scientific study of organisms and their relationship to the physical environment.
Excellent. What does dynamic mean? Change.
Organism.
All right? The organization of the biosphere from top down, from the highest level down, we start with the biosphere. The biosphere is made up of what?
Every living organism.
Well, what is it made up of? And organization-wise?
All its living things occupy.
All right? It's made up of what? Biomes. Biomes are made up of what?
Ecosystem.
Ecosystems. Ecosystems are made up of what? Communities. Communities are made up of?
Population.
The populations are made out of? Individuals. All right, so let's go back. We know what a biosphere is. What is a biome?
A group of ecosystems which share a similar climate.
Good. What's one biome?
Tundra.
Tundra. What? Rainforest.
A lake. Desert.
Lake. What?
Desert.
Desert.
Woods.
Woods. All right, jungle. Good. Those are all biomes. What is an ecosystem? Good. All the organisms that live in a place together in their physical environment. What are some ecosystems at this school? What are some ecosystems? Us. At this classroom. What else? The desk could absolutely be a biome. Back when we had desks that had, we used to have book things in here.
Yes, they put it in.
Trust me, there was bugs would get in there. It was awful. That's why we got rid of it. Cleaned out. Bathroom's a huge ecosystem. Okay. What is a community?
Different populations which live in a
Good. Different populations. Populations have to live in what? What's one word we use for that?
a country, state.
Now,
What?
what a community? What do?
Together? Lion? Lion?
It just looks like you're stretching.
Balance.
Oh.
I didn't fall down that whole time. Pretty good for an old man. All right. Good. All right, that's pretty good review there. Kind of brought us back up to speed on everything. All right. So let's talk about what a species is. We talked about the individual and the group. So now we're kind of gonna kind of move back up. Species. All right. A species is a group of individual organisms By the way, we just had a review. That means we're probably going to have a what tomorrow?
Quiz.
Okay, just so you know. A group of organisms that can breed. Sorry, lost my spot there. And produce similar offspring. All right? In other words, if I breed a male dog with a female dog, I'm going to get another dog.
What happens if you breed a dog and a cat?
Can't.
What you mean?
Can't. Doesn't work. It won't breed. They're not the same species.
But a tiger and a lion are not the same. A lion and a tiger are not the same.
They are not the same species. They are a hybrid. We'll get to that. Alright. They are a similar species, but they're not the same. They can produce a hybrid. All right? So if I breed a dog and a dog, I'm going to get a dog. Cat and a cat, I'm going to get a cat. Now, all dogs are not the same. All right? If I breed a dog and a coyote, okay? Guess what?
Yeah.
I get a hybrid.
So when the tiger and a liger, the tiger and a lion, when they mate, they child can't have an offspring.
Correct.
Right.
They cannot reproduce. Okay? Tiger. A male tiger, now let's do the male lion. And a female tiger produce a liger. Alright? Cannot reproduce.
Lion, tiger, and liger.
Alright? Tigon.
What's the difference?
There's some differences. They're slightly different. The liger is the one that's captured everybody's imagination. The thing about ligers is ligers don't stop growing. Animals actually have we all have a hormone that kicks off in our body that tells us to stop growing when our bones get to a certain density and certain length, and they kick in and tells our bodies to stop growing and getting bigger. The thing about ligers is they're like have a hormonal problem where they don't stop growing and they get enormous. And that causes them to actually die. It's what kills them. They just get too big. But they get enormous, much bigger than a lion or a tiger. Yes?
Is a husky a hybrid?
No. Husky is not a hybrid. There are some wolf dog. There are some dog wolf crosses that can produce a new species. Basically, they can breed.
So what is a husky?
A husky is a husky. It's a dog.
How do they
A husky is a husky. It's a dog. I mean, it's what it is. Okay? Half wolf dogs actually, dogs and wolves are close enough that they can not only reproduce, but they can reproduce some offspring that are not sterile. Coyotes are not. But can crossbreed, they can actually crossbreed with wolves. And they do produce a sterile hybrid, but that sterile hybrid is both traits and it's larger than either one. Yes?
if I do wild dogs, can like a wild dog, like a regular dog, or something?
Probably not. I don't know. The specifics you got to ask somebody that was, specialized in reproductive ecology, but which ones can, which ones can't. But in order to be a species, it has to be able to produce similar offspring. All right. And if it can't produce similar offspring, it's not a species. All right? Questions, and this kind of brings us to the end of this part right here, which is probably where your quiz will end tomorrow. Your next test, let me write this up here while I'm thinking about it. Next test in here will be Monday. Bio test. Monday, that will be 9/14. Yes. What? Somebody have a question? Do what?
No, I thought about it. Never mind. I see it. Bio test Monday.
Yeah, Monday's 14th.
Monday?
Yeah. Next Monday. You got that?
This Monday.
Oh, he did? Oh, yeah. Oh.
I just left today out. We'll get over it. All right, everybody got that? Bio test Monday. All right, now, in the ecosystem, there's two factors. First factors are what we call biotic. Now, biotic contains the word bio, therefore you know that they are what?
They're living the bio.
Living. Okay? These are living. These are the living parts of the biosphere, biome, ecosystem, all the way down. All right? So anytime we talk about biotic factors, those are the living factors. Now, living factors can be anything from a mammal or large mammal species all the way down to bacteria. all the way down to things that break down other things, and fungi, and slime molds, and those are all biotic, okay? Those are all biotic parts. So everything that's alive, and everything that, and every level that we talked about, going from the biosphere all the way down to the individual. All right? The second part is the abiotic factors, and we hadn't really talked about these yet. Now, a little lesson in Latin here, and Greek. Anytime you see a or an, it means not. All right? Right? Anytime I see the prefix a or an, or ant, or anti, a, an, ant, antibiotic. Anaphylaxis, antibiotic, all right? All those things mean not or against, all right? So in this case, it means not. So abiotic, if biotic is living factors, abiotic is what? These are your non-living factors. All right, so anything that falls into the abiotic part of biology is what we call abiotic. These are non-living factors. The biosphere, biome, ecosystem, etc. All the way down. So let's think about it for a minute. Put some thought to it. How do abiotic factors affect our biotic factors? First of all, what are some abiotic factors of an ecosystem?
A rock.
A rock. Absolutely. What else? Do what? The wind.
Air.
What else? Huh?
Is it like
The
soil?
black stuff on the table. What else? Soil. Your soil energy. The amount of energy in your soil. What else? Water.
These desks are living.
Nope, desk is not living.
And we're still talking about abiotic factors, right?
Yeah, abiotic factors. Chair.
That camera not living.
Camera.
That water rocket.
Pencils.
The rockets, they're not living. The Chromebooks, those all, I mean, and you brought it down to the classroom. That's a great way to think about it. If we think about this classroom as an ecosystem, all of the stuff that ain't alive, right? The board, the writing on the board.
Everything except for the.
Yeah, well, yeah, no, there's some other living stuff in here.
Bacteria.
We got a lot of bacteria.
What's the
There are, what? What? You got more bacteria living in your mouth and in your gut than there are people in the state of Georgia.
Oh, God.
You.
I'm going to do a virtual.
It's gross. It ain't gonna help you. You're just gonna have just as much. That doesn't change. Okay? We're giant germ factories.
Doesn't some of it benefit us though?
Absolutely. Some of it you could not live without. Some of it you couldn't live without. Matter of fact, if it wasn't for some of it, bacteria on your skin actually keep you from having body odor. Some of them cause body odor.
Is there a bacteria? What bacteria causes it?
What bacteria is it? I don't know. It is a bacteria, though.
You said it probably causes infection.
Yeah, absolutely. Some of them, if you don't have them, if you don't have enough what are called Langerhans cells in your skin, and these are not the same Langerhans cells that are in your pancreas, there are certain Langerhans cells that if you don't have enough of them, allow certain bacteria to build up on your skin that can cause infections, and those infections can become fatal. Because one of the things that those Langerhans cells do is they fight something called staph infection. Anybody heard of a staph infection? Yeah.
No.
Staph infections can be deadly. There are types of staph infections that people get that cannot be treated. Heard of MRSA? You know what MRSA is? Multicillin resistant staph. And basically it is a type of staph infection that you get, and it gets into your blood, it goes systemic, and you end up in the hospital on an IV drip of vancomycin, and it's not fun. And this stuff exists, it's out there.
Are you speaking from experience?
Huh?
I feel like how you know all this? I mean, I said, how you know all this stuff they're gonna hook you up to?
How do I know all the stuff they have to hook you up to?
Yeah, no, I'm talking about like, you said they gotta hook you up to an IV.
Vancomycin. It's an antibiotic.
Very true.
Okay?
Hey, that's all we know.
It's an antibiotic. Vancomycin is the strongest antibiotic that you can be put on. And if you're on it, you're probably in the hospital dying.
Do it save lives?
It does save lives. It will save your life. It will not cure a virus.
I was just gonna ask that.
But yeah, no, antibiotics don't work on viruses. That's one of the things, and we'll study that later. Do what?
So the virus is gonna be sitting there in your body.
Virus your body has to fight off. I mean, that's the only way you can really get rid of it. And cure a virus is your body's got to fight it off. They can create vaccines, but even vaccines are not 100%. Body doesn't always respond to a vaccine. There have been, some vaccines that have been very successful. Smallpox, very successful vaccine. There have been some that have been not quite so successful. I had a lot of problems with the chickenpox vaccine initially. With it wasn't really producing enough effect to keep the kids from getting it. Later on down the road, a lot of those young people that got that first round ended up with something called shingles, okay, which is the same thing.
But smaller and it's more deadly.
Do what?
Basically, shingles is smaller and more deadly.
It's not so much that it's deadly, and really it's just like chickenpox. Chickenpox isn't very deadly, but it's painful. Oh my God, shingles is painful. I had my brother got it, and I mean he was just miserable. It was like he said, it felt like his sides were on fire all the time because it's called something called neuralgia, which is nerve pain. There's basically the shingles, the chickenpox shingles get into the nerve roots and send pain signals. Really painful.
Can you still get the shingles today?
Oh yeah.
Are there vaccines?
Of all of the diseases that mankind has ever faced, from bubonic plague to Ebola to the common cold, humankind has only defeated one disease, and that's smallpox.
So is there a vaccine for chickenpox and the other?
Mm-hmm.
What's the other one?
So is that it's like chickenpox where you like get your eye and your little red dots all over you?
Yeah. Yeah.
Shingles is basically chickenpox.
Shingles is chickenpox inside your nervous system. And it's really painful. It's like I said, people that have had it describe it as having your flanks, that's usually in here. It just gets inflamed, and they said it feels like you're on fire. It says it feels like you're burning from the inside. Really painful, annoying, and it's not a fun thing to have. So back to abiotic factors. Just remember, abiotic factors. These are non-living factors. Think of them like this. These are physical elements that are non-living. And, I know that sounds redundant, but, the point is to make y'all understand it. Biotic factors, obviously, are the things that are alive. What are some things, now let's go outside the room now. Let's go outside the classroom. There's a lot of things that are biotic factors that create abiotic factors. All right? Biotic factors such as turtles, snakes, bacteria, these can create abiotic factors by doing things like digging holes that other animals use as shelter. Bacteria that was once living and is now dead, so they break it down and return the energy to the soil. So there's all kinds of things that biotic factors can do that create abiotic factors. Yes?
Isn't your parents a biotic factor?
They are a biotic factor. All right?
Alright.
And think about it. Your parents create abiotic factors. Like taking away or grounding you. That's an abiotic factor in your life, right? That's a biotic factor creating an abiotic factor. Abiotic factors affect biotic factors by determining what can live in an area. Things like weather. Weather's an abiotic factor. All right? Don't see a lot of penguins here, do we? Penguin is not a native species. No oceans full of fish and krill for them to eat around here. They like to live by the ocean. So, not going to do very well here. The abiotic factor is limited. Yes? Yes. All right? So, lots of abiotic factors. Anybody seen a herd of buffalo moving through recently? No. Why don't buffalo roam through the southeastern plains?
They ain't got nowhere to eat. They
ain't got enough to eat. Okay? Nothing to eat. The land is not really high heat year round. You've ever noticed they're very shaggy? Okay? Yes?
Eventually, over time, let's say I took a buffalo, it dies here, and I move another one here, and you know how it evolves to adapt to its climate, but it still has nothing to eat. So eventually, when it just starts eating humans, because that's the only thing
Well, the thing about buffalo are they're herbivores. They don't digest meat like we do, nor would they. Their stomachs are not made for it. Now, if you created some type of, if the buffalo had a mutation and first grew the teeth to be able to eat meat, they don't have actually the right type of teeth to eat meat, and the stomachs to break down meat protein, then yeah, it might happen over a long period of time. There have been, and here's the thing about predators and animals that eat meat. There's always a 10-to-1 you need 10 herbivores to support one carnivore for a year. All right? So you can't have that many of them. You've always got to have more, and we'll talk about that when we talk about trophic levels of energy in the ecosystem, but ecosystems have to have a certain amount of energy that moves up. Okay? And at the bottom are your producers, and at the top are your apex predators, your bears, your cougars, your mountain lions, your bobcats, depending on where you're at. And depending on how many levels you go up, there's less and less energy available. Most energy is available at the bottom. And one of the things that if you had buffalo, you would need large grasslands. Well, the southern climate it's not really grasslands, although we have created some through farming and clearing of trees. But most of everything below the Appalachians is what? How would you describe our natural landscape is what?
Grassy.
No.
Dry.
No, it's not really dry. It's only dry in the summer. It's usually wet in the winter. But think about what type of plants do we mostly have? What grows in Georgia and Alabama and South Carolina and Louisiana? Trees. Trees. Southern forest. Okay? Trees. This is a forested area. All right? Which is our primary herbivore that we have in Georgia. It's the one we have the most of. In fact, they are overpopulated to an extent. Now, there was a time, I remember, when, we went and got your hunting license, you got 3 tags a year. That's all the deer you could shoot for a year. And hunting licenses were limited. Once they got to a certain amount of sales, they stopped. And if you didn't get one, if you didn't go get one on the first day, you might not get one. So, now I think it's in Georgia, it's like 1 a day or something. But you have to tag them. And I remember when it had gotten out of control, and now the deer population is just exploding. I mean, it was rare, to see a deer anywhere outside of somewhere that was pretty rural back in the day. Now we got deer walking around cities. They've populated to the point they've grown into the suburbs and the cities. And they're just everywhere. Why?
Because
When you cut out people across the road.
Because they cross the road, cross the street.
I thought it was a white deer.
White-tailed deer.
Oh.
Yeah. White-tailed deer is the deadliest animal in America. Because people hit them in their cars and they go off the road and end up, getting killed. They're dangerous. Okay? That's why we constantly try to keep populations in check. Yeah. All right, so keeping populations in check is really important, and that's part of that balance we talk about in the biotic and abiotic factors. Think about this. Water quality. You know, water quality is one of those things that makes a difference in what is able to live in an area. Water quality with, you know, in the, let's say, North Georgia mountains is pretty good. What about the water quality of this river that runs by us? Chattahoochee.
No, because people have died in there, like multiple people. So it's
Oh yeah,
a little unhigh polluted.
it is. But here's the thing. Coming out of Atlanta, the Chattahoochee River is filthy. As a matter of fact, the city of Atlanta pays $100,000 in fines every day to the EPA for polluting the Chattahoochee River. All right, so coming out of Atlanta into South Fulton, Coweta, and Troup counties and Heard County, it's a gross, nasty river. I won't go in, I won't swim in it up there. Then we got, let's see, what is that lake? Lake West Point. West Point helps clean the river. And then the water comes out of West Point and goes to Lake Harbor. And Bottoms, and then finally at North Point, or South Point Dam, North Point Dam, you have the final piece. And then the river's actually pretty clean, running past Columbus all the way down to Eufaula and mostly all the way down to where it empties into the Gulf. Much cleaner. So there are natural systems in place that actually help clean it up a little bit before it gets to us. Now, north of Atlanta, it's a very clean river. A lot of that's due to a group called the Upper Chattahoochee River Keeper. But the city of Atlanta is just not doing its part in taking care of the river. And it's just, you can't even eat the fish anywhere south of 285, and certainly not south of I-20, all the way down until you get to West Point, and at West Point they even recommend that you only eat 3 a year, and that's because of toxins and mercury, lead, and other things that are in the water that build up inside of those fish. So you got to keep them clean. You got to keep those rivers clean. Water quality is a big deal. Now, it's not always humans that pollute water. Abiotic factors can pollute water too. The sulfur and things that come up in a place like Yellowstone. There are pools of water in Yellowstone that kinds of bad chemicals in them. But guess what? Stuff grows in there. They have found alkaline, highly acidic ponds. So even though that water would be toxic, so abiotic and biotic factors work together to keep ecosystems healthy. Okay? Anybody got any questions?
Can abiotic factors like rocks? Not
I mean, rain, that's erosion. Things like that certainly matter. Okay? Weathering. It helps. It puts more energy in and makes more energy available to other things. All right, let's go ahead, y'all. Take your desk off so I can go ahead and spray down. Don't line up the fuel. Or you just going that way. Grab the thing right there. trouble. Don't do anything stupid.
Morning.
What's happening?
Not much.
All right. Plug this in. And go plug this in. Good morning.
Cool.
Hey. I got you. Alrighty.
What, you got me today? Is it coffee? Is it baby? What, 2K7? You think 20's better than 2K17? Yeah.
Now I'm gonna start saying that.
Not, but
Alright, y'all, let me get rolling here real quick. Let's see, Canyon.
Here. 2K16. Here.
Yeah. Bang in your chair. Alex.
Here.
Bonnie.
Here.
Tyler.
Here.
Austin. He is legal. Sydney.
Here.
Jason. Emerson.
Here.
Travis.
Here.
Frank. Diana.
Here.
Will.
Here.
Steven.
Here.
Tucker, I mean, Elliot.
Here.
Quavion.
Yeah.
Quay.
Here.
Ramos.
He's online.
Ramos is online.
Yeah.
Creation.
Here.
Karina.
Here.
Kayla.
Here.
Gavin. Juan Carlos.
He's not here.
Will.
Here.
Davin.
Here.
That's.
All right. Now I've got to do something else. Everybody have a good break.
Yeah.
Says I'm live. I don't know. All right, let's go back. Let's do a quick review of things we were doing before we left. Just to make sure we're all caught up. We're doing a review over things today. What does that probably mean we're going to do tomorrow? No. Next test in here will be Friday, probably. All right, so what is gravity? What is gravity?
Force acting between two masses before they close together. Force acting between two masses before they close together.
Good. It's a pull force between two masses that pulls each other together. All right. Every mass has a force of gravity on every other mass. So everybody in this room is actually producing a force of gravity on everybody else in this room. And your desk. And the walls. And they're all producing, sending a force of gravity back on you. Right? Is gravity a really powerful force?
No.
Not really. Not really. It goes for miles and miles, and it goes forever. But gravity is not going to pull us, even if we're in deep space and we're only 5 feet apart, it's going to take us 5 hours to accelerate together. All right? What is more important when measuring gravity, the mass or the distance between them, as far as feeling gravity? The what? The distance between them. Why? Why is the distance more important as far as what you feel as far as gravity? Look at the formula. Look at the formula and tell me why distance is more important.
Gravity walks both time and space.
No?
Bro, I can't read my handwriting.
Look at the formula for gravity. Remember, big G times M1 times M2 over D squared. Why is distance more important? Just look at the formula. Force of G equals gravitational constant times mass 1 times mass 1 times mass 2 over distance squared. Why is distance more important?
Distance has a greater effect than mass on the effect of gravity.
Why?
It's exponential.
It's exponential. That dude right there.
That word is not.
All right? Because distance goes up exponentially. All right? Masses are only multiplied. All right? They go up only by their size, only by the amount of mass available. All right? So if I double the mass, I double the force, but if I double the distance, I quadruple. Or half the distance, I quadruple the force, or reduce the force by a factor of 4. All right? So distance is the bigger element when feeling the force of gravity. Did I give y'all the gravitational constant?
Yes.
Okay. What is the gravitational constant?
6.67 times 10 to the negative 11.
Right. That's not very much, is it? Times 10 to the negative, that's
That's like
667. 11 zeros is what? 10 billionths of a kilogram per second. That's not very much. Time, what's the standard unit of measurement for time? Seconds. Did I talk about the cesium atom?
kind of, yeah.
Atomic clocks?
No, he did.
Did I?
Constant. Yeah.
Alright, so what atom, I already just told you, what atom does a atomic clock run off of? Cesium atom. What happens to time as you move through space?
It changes.
The faster you travel through space, what happens to your
The
time?
slower your time.
The slower you move through time. What is inertia?
You don't move unless something moves you.
You don't move unless something moves you. That's a pretty good way to put it. What does the actual law say? A body will stay at rest or
Or a body in motion will continue.
in motion in a straight line unless what happens? What does it got to have? An unequal what? Force. Good. Newton's first law. All right, what is the force that keeps things in orbit? Why doesn't the moon just fly off in a straight line? Come on now, we only got 3 subjects we're working with right here. It's got to be one of them. What is the force that keeps objects in orbit?
Acceleration?
No. Gravity. All right. Remember, gravity is the force that keeps it in motion. That is the unequal force. If all forces were equal on the moon would just go slinging. All right, it would just be slung off. So here's the Earth. All right, here's the moon. The moon goes round the Earth, right? That's what it does. All right, if there were no gravity, if we suddenly shut gravity off, wherever the moon was at that point, it would just go. So the unequal force is gravity. All right? Gravity, little g, is our unequal force. All right? It pulls the earth towards the moon, or pulls the moon towards the earth or around it. The earth also feels an equal what? Tug of what? Pull of gravity. So they're both feeling each other's gravity. So yes, it does make the earth wobble. We'll talk about the wobble of the earth's spin and how it wobbles a little bit in its orbit later and what that causes. But there is a little bit of wobble because they both feel the same amount of attraction. All right? The moon is trying to move in a straight line. All right? Gravity keeps acting on it, keeping it in orbit. All right? What do we call this change in direction and speed? What is that called?
That's easy.
Y'all are taking physics with me too, most of you. So what is a change in motion? or direction called?
Displacement.
No, displacement.
Acceleration.
Huh? Acceleration. All right? Any change in direction or speed is acceleration. So what we're really seeing is the moon is accelerating around the earth. All right? It's actually acceleration because it is change in motion, is actually a change in direction that force causes. All right? Let's see, we've already talked about that. Are weight and mass the same thing? What is weight?
Oh man.
Weight is the effect of gravity on a body.
Weight is the effect of gravity on a mass or a body. All right? Let's see. What is surface gravity? That's easy. I know you know. Trying to get some of these other folks to chime in here. What is surface gravity? Come on, the definition's in the word.
Gravity of a surface.
It's the force of gravity felt on the surface of a planet. All right? Different planets have different gravities. All right? Different planets feel different gravities. Different bodies. There's 1/6 the pull of gravity on the moon as there is on Earth. All right? So there's 1/6. Now, if we look at this, understand this. Okay? This gravity thing and this constant, if I weigh 100 kilos on Earth, right? That is my weight. 100 kilos on Earth. On the moon, which has 1/6 the gravity, what is my weight? How much do I weigh on the moon if I weigh 100 kilograms on Earth?
Like 18 pounds.
That's so random.
So we can just,
You will weigh 16.7. Well, 16.6666.
1 over 6 equals, and then that's 100 over 6.
16.6.
16.6 kilograms. All right, on the moon. So my weight goes down. Right? If I'm only feeling 1/6 of the pull of gravity. All right. And gravitational fields. All right. If I have two planets, we're still talking about surface gravity here. And the mass of this one equals 1, and this one's smaller. The mass of this one also equals 1. Which one is going to have the greater surface gravity? The smaller one. Okay, this one will have greater surface gravity. Why? Think back to what we talked about earlier. What's the biggest factor in how much we feel gravity? The mass or the distance?
Distance.
The distance. And in this one, I am closer to the center of gravity.
Ah.
All right? So if I'm farther away from the center of gravity here,
Way less.
way less, okay? The effect of the gravity will be less. So we're still talking about surface gravity, all right? If they're the same size and whichever one is, if they're the same size and one has greater mass, then the one with the greater mass is going to cause me to feel more gravity. What are Kepler's 3 laws? First one, all planets have what?
Orbital.
Elliptical orbits. All right. Law number 2.
Orbital speed varies.
Orbital speed varies, and if a planet covers the same amount of space area in its arc, it'll be the same amount of time. And number 3.
Amount of time it takes a planet to orbit is related to its distance.
Good. Amount of time it takes a planet to orbit is related to its distance. What is escape velocity?
The velocity it takes for you to get the atmosphere.
Good. Well, to get away from not the atmosphere,
To get out.
what are you trying to escape?
Gravity.
Gravity. That's the amount of speed it takes for you to get away from the amount of gravity. What is the Earth's escape velocity?
Like 98.
11
Oh wait, kilometers per second.
11 kilometers per second. What is the sun's escape velocity at 1 AU? At 1 astronomical unit.
Kilometers.
42 kilometers per second. All right? Why are black holes black?
It's like that.
Why can't light escape?
Escape velocity.
Because the escape velocity is greater than the speed of light. All right? What type of energy is light?
Radiant.
It's radiant. That means it can travel through space without what? Without a medium to carry it. All right? It doesn't need air or anything to vibrate to pass it along. It's just a wave. Let's see. What's the speed of light?
Too fast.
300,000
300,000 what?
per second.
Kilometers per second. It's actually 299,792.458 kilometers per second, but we're not going to worry about being that detailed. Anytime, what letter do we use to represent the speed of light?
Oh, E.
See?
C.
Oh.
E is energy.
Shut up, Chris.
E is energy. M is
Mass.
mass. C is the speed of light squared. Let's see. What do we know about the speed of light?
Nothing.
Nothing can exceed that speed. That's our absolute speed limit, right? Let's see. Is it a particle or a wave?
It acts like a particle.
Acts like both, all right? But it is a wave, and it also acts like a particle. Okay, so there is a light wave, there is an electromagnetic wave, and there's also a photon or particle element to it as well. Let's see. Visible light is what? Part of the what?
Electromagnetic.
Electromagnetic spectrum, good. Let's see. What are the important properties of light? I gave you two.
Do not interact.
Well, no, it doesn't. Good. It doesn't interact with what?
Matter.
Matter. But that's not two of the properties I gave you. Visible light is always between the wavelength of what and what?
400 and 700 nanometers.
400 and 700 nanometers. All right? So if those waves are bigger, okay, if they have greater magnitude, each wave, what does that make the light? What does that do to the intensity of the light?
If you what?
It brightens it, okay? It brightens the light. What's the other part of light's wavelength that's important? Brightness and if we bend light, what does it do?
Scatters.
Scatters and becomes different what?
Colors.
Colors. So brightness and color. All right? We can learn a lot about light between brightness and color. Remember, our sun gives off white light, right? Some give off red light. What does that tell us?
Cooler.
They're cooler. Some give off bluer light. What does that tell us?
Hot.
They're hotter. All right. Let's see. What about, did we talk about pigments yet?
Yeah.
All right. What's a pigment do?
It absorbs color.
It absorbs color. All right. That brings us up to date.
Wait, can I go to the bathroom?
No.
I mean, you're going to miss all the new stuff, but she's not going to give it to you. She ain't going to let you. She ain't your keeper. Hurry up. All right, the electromagnetic spectrum. Now, we know that there is this middle area in the electromagnetic spectrum that we see. All right? And it's a very small sliver in the electromagnetic spectrum, and we call this visible light. All right? So this really small, slim area of the electromagnetic spectrum that we can see. Those wavelengths between 400 and 700 nanometers, we see them as visible light. All right? That's a really small area of light that we can see. And if we made a continuation up here, what we would see is that there would be very long wavelengths on this end. And those wavelengths would get smaller and 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 smaller until they're extremely small way out there on the end. All right, the wavelength is here. Okay. On our wave, all right? So that's our wavelength. It goes out to very, very long waves, and it goes down to very, very tiny waves. Remember, visible light is between 400 That's pretty small. Well, some of these out here are miles long. All right, some of these out on this end are miles long. And we'll go this direction first. We'll go towards our larger waves first. All right, our first set of waves that we come to in this area okay, are called infrared waves, right? This is the infrared spectrum. INFRARED. Infrared. Right? That means they're longer than the red waves, right? Because our red light is over here. On this end is our red. And our violet is at the very end. All right? So this FRA, sorry. FRA, infrared. So on our infrared light, we feel this is heat. So even though we can't see infrared, we can feel it. It has practical purposes. This is what your TV remote runs off of. Your garage remote control runs off of infrared waves. Pretty much any remote control device, most of them run off infrared waves. The really simple ones. You can use different waves for different things, but most of them run off of some type of infrared. So tonight, when you're at home and you're flipping through channels, trying to find your favorite show, what's y'all's favorite show? What?
Big Bang Theory. Big Bang Theory.
Big
Bang.
Bang Theory. I hate math. I literally have a hard time talking to people with math because I can't see your lips, and I rely on that. So if I ask you over and over to say something, it's not because I can't hear you, it's because I can't hear you. I'm not saying it was aliens. It was aliens. Anyway, yeah, Big Bang Theory. So you're flipping through tonight. When you're flipping through, trying to find Big Bang Theory, which is a good show, by the way, makes me laugh, to your TV. All right, that's infrared. It has purposes. And just because we don't use it doesn't mean other animals don't. Animals like snakes.
No way. Snakes are remotes.
Snakes are TV remotes. Snakes use infrared.
You don't know what a joke is? Not funny. You have no sense of humor. Humor is a joke. If I would start crying.
So they can use infrared to locate prey. They can see heat. They have sensors in their nose and mouths that can basically see heat, and they use it to locate prey. All right? And in complete and total darkness. Have y'all seen the military infrared images?
Yeah.
Where they're where guys are trying to hide, and they're like, "We see you," because they have infrared. That's what a snake sees. A snake can do that all on its own. See in the dark with infrared. Okay? And locate prey in total darkness. Can't see anything, but snake can bite you anyway. All right. After that, this section right here, let me erase this. And this is, it's strange that we call them this because you would think they would be smaller. All right? You would think they would be smaller. This is the microwave zone. And of course, micro means what? Tiny, but they're actually longer, bigger waves than infrared. All right, they have a longer wavelength. So they're going this direction. They're actually longer waves. Microwaves have purpose too. All right? What microwaves can do is vibrate water molecules. So if you want to know why microwaves make food hot, it's because they vibrate the water molecules. And that increases heat. In the water and can be used to cook. I got to get some different markers. I don't write as big with these. So we can actually use it to cook. So when you put something in a microwave and turn it on, what you're doing is you're bombarding that piece of food with microwaves. And those microwaves are vibrating the water molecules, and when molecules vibrate, they heat up, causing the electrons to jump out to higher quanta or higher levels of their valence shells, and that increases their heat, increases the amount of energy. So what you're doing is you're boiling the water inside the food. That's what heats it up. All right? Microwaves are really important in astronomy. Because we use microwave telescopes to study the early, where am I right now? The young, let me write young is a better word. The young universe. A couple guys figured this out because they kept having problems with a receiver, which was supposed to receive wavelengths from short radio wavelengths to longer microwave radio wavelengths. And they kept getting this buzz. They said, we got to get this hum out of this thing so we can see what's going on. So they cleaned it. They thought that the problem was that pigeons had pooped all over it. So they went up, cleaned it up, made it nice and shiny, pointed it back at what they wanted to point it back at, and boom! Right back to the same background static. What they were really seeing was the leftover remnants of the heat of the Big Bang. And you can see this when you turn on a TV, on an old TV, on a station that doesn't work. If you've ever used an antenna or a VHF or a UHF or a VHF TV and went to a channel that wasn't working and there was static, same thing. That is literally leftover heat waves from the Big Bang that are flying through the universe. That's what causes that static. So microwave telescopes are really, really important. All right? That brings us out here to some really long waves. These can be kilometers long. These are radio waves. Way out here. Radio waves can be really, really, really long. We have a lot of uses for what radio waves. The radio waves were some of the first discovered. They have a wavelength greater than 1 kilometer. And that can go out to even longer and longer and longer. Radio waves obviously are important for communications. Now, all wavelengths in any of these areas, all the wavelengths are not the same. Okay? So we have a couple different ways of using radio waves to listen to the radio. One's called amplitude modulation. The other one is called frequency modulation. And this goes back to our wavelength right here and our wave height. All right? Amplitude modulation is obviously what kind of radio? AM. Frequency modulation is FM, no static. All right, FM radio. All right? Now, in amplitude modulation, your radio distinguishes the channel by the height of the wave. So all of the wavelengths are the same, but one may have a very high amplitude, all right? Another may have a very low amplitude, even though the wavelengths are the same, all right? It's the height of the wave. That is the amplitude, all right? So the height of the wave equals amplitude. AM radio can carry a long, long way, but it is more sensitive to weather and static and interference. You can pick up AM radio stations if y'all, I don't even know if anybody even has an AM radio anymore, but you can pick up AM radio stations from all the way across the country. All right? AM radio can carry a long, long way. And it might be spotty. You might be able to pick up a channel from Illinois one Friday night. But you can only pick it up near Columbus. You can't pick it up in Phoenix City or Talbotton or anywhere else. Okay? So AM is sensitive, a lot more sensitive to external interference. Now, FM has to do with frequency modulation. So the frequency has to do with how often and how long the frequency of each wave comes through. All right? And the frequency of the wave passing through is the same, and the frequency is different. All right? The frequency is the number of waves passing through a given point per second. It's called a hertz. All right? So if I'm listening to something on 95 megahertz, that means it has, what's mega? A million, right? Okay? 95 million waves pass through that point each second. If I'm listening to something at 80 megahertz, then 80 million waves are passing through that point per second. All right? That has to do with the size and the speed of the wave through the point. All right? And the speed actually doesn't change because the speed is what? It's the speed of light. All right? Radio waves also gave us radar. All right? Obviously, radar has been really important in communications. Radar has been really important in air travel. Radar has been really, really important in doing things like, winning World War II. Okay? So radar works on radio waves. It works by sending out a radio wave, bouncing it off an object, and seeing how long it takes for it to come back. All right, so radar is a great way to find where something is. All right. It is also important in astronomy. All right. Radio telescopes help find forming and exploding stars. Because usually the first waves they give off are either radio waves. All right? Now, all of these waves pass through us all the time. Okay? And these are our longer wavelengths. These are longer than our visible light. All right? Then we have 3 sets down here as well. All right? First one is what we call the ultraviolet. All All right. Ultraviolet because they're on this side of the violet spectrum of the visible light. Okay. Infrared goes with these longer red blinks. Ultraviolet is on the other side of the violet that we are able to visibly see. All right. Ultraviolet waves have a lot of purposes that we use them for. Ultraviolet, that's what's in your tanning bed. That's probably the place you think of them the most. The sun also gives off a lot of UV light. The sun also gives off lots of UV light. That's what gives you a sunburn, gives you a suntan. In astronomy, ultraviolet telescopes, they are good for detecting low visibility stars. So there's a lot of stars out there we can't see very well. But you can take an ultraviolet telescope and it can sense the heat coming off of it. If you've ever seen an ultraviolet, and we'll look at some of these tomorrow, ultraviolet telescopes, they can artificially color them and you can see these red dwarfs and very low intensity stars. And this is going to be something that you're going to see over and over and over. Ultraviolet rays cause cancer. All right? And we'll get to the other two tomorrow. Y'all have a nice day. Stay out of trouble. Don't do anything stupid. Don't do drugs. Drugs are stupid. Don't do drugs. Drugs are bad. Drugs are bad. Don't do drugs. Drugs are bad. Y'all behave. Yes.
I just want to let you know, tomorrow I won't be in because I'll be down in another meeting center for the next meeting. No problem.
You have to be on when the car stops because otherwise, like it has to keep turning, but then it's not being powering anything, and if it was, it would just end up, like braking itself because you're powering against the brakes. So it's trying to move an immovable thing. So then, do they just get disconnected and let it run when you're at a stop?
Do you want to turn your side up or are you?
Can I go to the restroom?
Hang on, I got 9 million things here.
Alright. Now you dress him up? And then come back?
Yes.
Alright.
Shoulder. You brought your guitar and awesome the guy.
I actually brought it Friday.
Oh. Who likes why? I was working out this weekend and playing chest day, bro. Oh, do you not do chest day? I run cross country and track. We go to chest day. So you need to. I don't think you do. I need to, but I don't. You really should. I probably should. But curls.
Sounds like coffee. Oh, Bradley, you're on the Mevo.
I don't think it's on.
It is on.
Red.
That means it's on.
Stop.
Red means recording.
No, I mean,
Daddy, nobody won't look at you.
Oh, it's right here.
I just want to eat lunch. I don't want to.
extremely skinny. And then just being
Did you say you don't want to eat lunch?
we're talking about how I don't
What is this?
Hey! Alrighty.
not at all like
Alright. Alright, look, foot bag's got to go in the back. Put the foot bag in the back.
Is mine?
Put it in the back. Get it out of the way. Yes. Yes. I don't care. What makes you special? Nothing. You have to follow the rules too.
I don't have a partner. That's what I
she actually
That's a you problem. Oh yeah. Put your foot bag in the back.
it's not funny. It's hilarious.
Foot bag in the back.
They're going, I promise.
Oh.
She took just top
Don't drive me crazy. All right. I will come in this week.
no longer has Hot Wheels. It's entirely Olivia's fault.
All right. Let's see. Joe.
Here.
Neil. Claire.
Claire.
Hey, listen. I need y'all. We're gonna have to do this every day for a while. I gotta figure out who's on here and who's on here, so I can send out the invite. Claire.
Here.
Anna.
Here.
Jonathan.
You don't know
Jonathan
Yeah,
Davis.
I know.
Yes.
Matt.
Hello.
Joseph.
Here.
Jackson. Lucas. Lex.
Present.
Tristan. Alright, he's on here.
Tristan, like, wait, what's her name? We're trying to do 30 minutes.
Alright, so, I do that, and I do that, and I go,
Her dog. Hashtag dog.
alright, so Tristan, Alyssa,
Here.
Gabriella,
Online.
that's her right here, alright, Olivia,
Here.
Isis,
Here.
Creation,
Here.
Isabel,
Here.
Jonathan,
Here.
Mallory,
Here.
Matthew,
Here.
Sophia,
Pugs.
Wells, she,
They're not hissing. You bark. I don't hiss.
and Zach.
Just say for the whole time, like,
I was at different kind of games.
So, we should be rocking and rolling here.
I'm just used to TV.
All right. I hate changing gears every day. It's a quick shift.
That's why we should get the same setting.
that's why you usually like. Not automatic.
All right. So let's do this. Let's go back because we're about to put a bunch of things together. All right. Let's go backwards. Let's go backwards. All right. Look at your notes. Open up your notes real quick. Let's review what we're saying.
It's not very hard.
I was thinking about how to.
Yes, I did.
They call you UV.
So I did it fine.
Because you cause cancer.
That's my favorite one. Yeah. I like that. I like that one.
Why is your book bag still in the front of the room?
There's literally one roll. It is.
Right. Okay. What is motion?
Change in position.
All right. What is straight line motion?
Change in position is one
Directly between 2 points.
Directly between 2 points. Good. What is the motion diagram?
It's like you draw.
It's where you're
Drawing.
It's where you draw pictures, series of images. What is the particle motion? Particle diagram.
Place an image with a single point, usually in the center of mass.
Very good. What is a coordinate system?
It's
It
like
shows location.
It's a graph. Okay, that's good enough. What is the origin?
0.
Zeros. What do arrows show? What is the magnitude? The size or quantity. What only has magnitude? Scalars. What has magnitude and direction? What does the Greek letter delta mean? What do we use X, Y, or S for?
S for displacement.
S for displacement, but it's also for a what? A position. Okay, so delta X means what?
Change in position.
Delta S means
Change in displacement.
change in displacement. Delta T,
Change in time.
change in time. God, y'all are fairly smart. What is the vector quantity for movement?
Displacement.
Time is always what? Scalar. A squared plus B squared equals C squared is the Pythagorean theorem. Pythagoras. All right. On a position versus time graph, what is the vertical component of the graph? Position. What is the horizontal component? Time. All right. On a velocity versus time graph, what is the vertical component? Velocity, and time is always horizontal. On an acceleration versus time graph, what's vertical? Acceleration. What's horizontal? Time. Time's always horizontal. On a time graph, do we need negative time? No, it doesn't exist. All right. What is speed?
Movement.
It is movement.
Movement in a certain direction. I am a speed coach.
Acceleration.
Methamphetamine. No.
I'm sorry.
What is speed? Speed is not acceleration. No, it's not velocity.
Speed is my entity.
It is the scalar quantity of velocity, yes. What is it equal to?
Total or no?
It's like
I know it's equal
Yeah.
to the slope of the tangent line.
It's the slope of what?
The tangent line.
The tangent line. Okay, what does that mean?
magnitude.
Hold on, I have it somewhere.
It's the what?
Actually, it's the
Change in position over control.
Rise over run.
Rise over run is going to give you the speed.
Can we call it flow?
Okay? It's the rise over the run. All right? Distance divided by time. All right? And here's the thing. This is where you get in trouble in physics. Don't make things more complicated than they are. Okay? Always bring them to the simplest terms. All right? It doesn't matter what level of physics you go to in college. I mean, you may be always bring things down, break them down by components, and make them easier. All right? All of your calculus that you'll take, all of your trigonometry that you'll take will make it easier if you know how to break down things to their simplest forms. All right? Those are tools. Those are things in your toolkit. All right? Bringing them down to make them simple as possible always helps. All right? Somebody told me this one time, long time ago. They said, you really don't understand a subject until you can break it down and make it simple.
That's why they say
Okay.
when you teach it, it helps you.
When you learn to make things simple, then you can teach them. Okay? I've had a lot of success in some areas of my life. It has been my ability to make them simple and understood by other people that have made those things successful. Okay? In coaching, it is not my vast experience of knowledge. It is my ability to take that vast experience and make it as simple as possible so that somebody that's never played a position or never done a movement can do it. Breaking it down. It works the same in academics, especially in math and physics. Get it down to its simplest parts, break it apart, and then put it all together. All right? And I found the same thing. I took, guys, just for y'all, because I love y'all so much, okay? I took 2 online courses in physics this year just to sharpen up my skills. And I kept making mistakes, and I was like, I got really frustrated. And then I went back, I said, okay, I'm going to go back. And I went to the Khan Academy course. And in the very first part of it actually wasn't the Khan Academy course. It was a different little physics video I watched. And at the very beginning of it, it said, don't let the math intimidate you, break it down. Same thing here. We're going to do, as soon as we get through this little review here, I'm going to show you how to break things down and how different graphs mean different things. All right? So speed is just right. Just remember, rise over run. Okay? It's just my slope. It's just the slope of my angle right there. All right? What is velocity? First of all, what is it? Velocity is a vector. All right? And it is what? It's speed and direction. All right? It gives me speed and it gives me direction. All right? If it's, let's say my velocity is positive, what is my slope going to be? Up. If my velocity is negative, what is it going to be?
Down.
Down. Okay? And to the left. All right? Let's see. What's my formula for average velocity?
XF minus S,
Position final minus.
or TF minus TI.
Good. Ratio of an object's change in position to the interval in which it takes place. Okay, so XF minus XI, X final, position final, minus XI, position initial, over time final minus time initial. All right? And we can find that anywhere we want to. So if you don't have that written down, write that down. XF minus XI over TF minus TI. All right? Let's see. What is average speed?
Your first point and your final point.
Okay.
Average.
Average. All right, but it's the average, it's the what?
Yeah, it's your rise over run again.
It's your rise over run, but speed is what? In mathematics, because it may not be, we may have negative speed, but we can't have negative speed, can we? It's the absolute value. All right? How can we get instantaneous velocity? Speedometer. Okay? And I can go through a whole series of things to tell you why instantaneous velocity is so hard. Even if we use a parabola, we still have to break it down to, you know, the smallest rise over run that we can, and we're still getting, even if we break that down to infinitesimal, that's the whole thing about the word instantaneous. Instantaneous means 0 time. So it's a very difficult thing to get. We can get really, really, really close within millions of a, meter per second. But we're never going to really get a true instantaneous velocity. All right? We can estimate it on a time versus position graph. But again, it is just a really, really, really accurate estimate. All right? What type of motion is acceleration?
Non-uniform.
It is non-uniform motion. All right? Acceleration is a non-uniform motion. What is uniform motion?
Time.
That means our velocity is never changing, right? So it's an object moving along a straight line, all right?
Could an average?
With an unchanging speed. So it's moving.
The average is that?
Oh, the uniform motion? Uniform motion, don't confuse the two. One thing at a time. All right? What does non-uniform motion tell me? We have a change in what or what?
Velocity or direction.
Velocity or direction. Good. Let's see. Motion diagrams for acceleration. Does deceleration exist?
No.
Not in physics.
Not in physics. Not in physics. All right? We describe things as decelerating, but as far as physics is concerned, it's simply acceleration in the other direction. All right? It's a decreasing acceleration. What is the definition of acceleration?
Moving forward or increasing movement in one direction or increasing speed in one direction.
Okay. I gave you a definition that you should have written down.
So a non-uniform motion, change in either velocity or direction.
All right.
What was the question one more time?
What is the definition I gave you for acceleration?
Non-uniform issue.
I gave you another definition. I know I wrote this down.
What's that?
All right, if I didn't write this down, write this.
Slow down.
Acceleration is the rate at which an object changes velocity over time. All right? So write this down as a definition for acceleration. That's what kind of go through these. Rate at which an object, let's say, changes speed or velocity. Yeah, an object changes velocity. Why can't we use the word speed?
Because that would imply you're not changing direction.
Because it's a
Because it's a scalar. All right, because acceleration is a vector.
Over time,
Right.
it just changes.
Just changing.
Okay.
Just keep it simple.
Acceleration is a vector.
Acceleration is a vector. All right? All right, so let's play with some graphs. All right, let's play with some graphs. Let's play with a little graphing here. Let's make first let's make a position, okay? A position versus time graph. And let's make a velocity versus time graph.
Are these representing the same thing?
Yeah, we're going to do the same thing on each one of these. This is velocity versus time graph. And then let's make an acceleration versus time graph. All right? And these are our numbers. All right? 0, this is our position. All right? And this is our time. All right? Let's see. And it should be written the other way. Time and position. 0, 0. 0. Let's see. Let's go 0, 10. Sorry. Let's go 1, 10.
Is this like a
2,
like a point? Like how you'd write parentheses X
20.
on the Y?
3. Let's go 40. 4, 55, and 6, 7. All right. So we can plot this easily, and this is how we can use a graph to move things over. All right. So let's start out and let's just plot it here. So at what we got? 6 seconds. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so on our time graph here, we start out, John. We can start out here and we'll make this, we go out to 70 here, so we'll make that 70. 1, 2, 3. Now we go out to 70 here. We'll make that 70. 5, 10, 20, 30, 40, 50, 60, 70. So we'll make each one of these 10, 20, 30, 40, 50, 60, 70. All right? So our first point is here. 0, 0. Our second point is 1 second. Our object had moved 10 meters. In 2 seconds, it had moved 20. In 4 seconds, it had moved 55. So 4 seconds, we go up to 50, and halfway is 55. That's more like 50. 55. And then at 4 seconds, at 6 seconds, 1, 2, 3, 4, 5, 6 seconds, it was going, that's a little bit long there. Got to make our spacing equal. It was going at
5.
Oh, I skipped 5,
Yeah.
didn't I? Lost my mind. 1, 2, 3, 4, 5 seconds. It was moving at 70. All right. So up here. All right, we can plot our graph here. And we can see things happening in our graph. It should actually make a curve like this. All right, so I may need to adjust these a little bit. All right. Five seconds there. And we can see that our position graph makes a slope, doesn't it? It makes a curve. It doesn't stay the same. All right? So it is constantly moving up. And we can see this on a position versus time graph. Now, this is going to tell us a lot of things right here. All right? We can get our average speed. Okay, we're going to say that these are all in the same direction. They are moving, let's call this east. All right? Let's call this east. All right, so at 10 seconds, we moved 10 meters, or sorry, 1 second, we moved 10 meters east. 2 seconds, 20 meters east. 3 seconds, we moved 40 meters east. 5 seconds, we had moved 55 meters east. And at 5 seconds, we had moved 70 meters east. Somebody must have hypnotized me and took the number 5 out of my brain or something. All right, keep leaving 5 out. Make that equal as much as I can. All right, so what can we learn from this? Well, what is my acceleration here? Or what was my next one? What was my velocity here between 0 and 1 second? 10. 10 meters per second. So 1, 2, make them a little bit bigger here. 1, 2, 3, 4, 5. So we know at 0 seconds.
How could I do this thing? Of course, you're not going to possibly do this. You're going to...
Got to work on my graph, Sean, don't I? All right. So what is my velocity here for the first second? What is my average velocity? What did we just say? 10 meters per second. So for the first second, all right, I can take my velocity here, and I know that my velocity is at 10 meters per second. All right, what is it for the second second? Does it remain constant?
No. Wait, well, in theory, yeah, it's supposed to. It just doesn't look like it.
All right, it goes from 2 seconds, 20 meters. All right, I'm still moving at 10 meters per second. So for my second one, my change here is still at 10 meters per second. All right? So I'm moving at a constant velocity.
Well,
I'm moving at a constant velocity at this point. All right? What about my third?
20.
20. All right? How many meters per second am I moving now between second 2 and 3? All right? So now I'm moving at 20 meters per second, 10, 20. And I can see now that my velocity is increasing. All right? I can see now that my velocity has increased over that amount of time. What about between second 1, 2, 3, and 4?
It's gone down to 15.
It's gone down to what?
Yeah, it's at 55, so it's gone down to 15.
It's gone down to 15 meters per second. So my velocity now has gone down in between, right? What happens to my velocity between second 4 and 5?
15.
It's still at 15. All right? So I can plot that velocity as well. Now, to find out what we need to be able to do, come here, now I can draw my square and I will get that 15. All right? This area plus this area. And what we'll find is that this is 10. This is a rise over run, 1/2, right? 1/2 the base times the height. And we're going to get 15 right there. All right? So on my velocity graph, I can still use the same concepts. And let's see, we dropped the 15 here. We can still use those same concepts. All right, sorry, that one was 20. We're going to find 10, all right? Here we're going to find 5. All right? That's not coming out right for me somewhere. All right, so we're going to get 10 and 5. And this has a lot to do with my graph, and we're once again going to get 15 here because we're going to have 15 over 1 is going to be 15. All right? But we can find all these things if it weren't for my crappy graphs I've drawn up here on the board. All right? We're going to find all of these equal out no matter what I do. So my time velocity graph, all right, I'm going to get the same numbers. Now, when I add this over to an acceleration graph, all right, and I probably should have done this one first. 1, 2, 3, 4, 5 seconds. Go down. Yes. Then this. All right. Should have done the velocity one first. I probably should have gone through velocity graphs in general first. Or sorry, acceleration graphs. What we're going to see on an acceleration graph is similar to what we're going to see here. All right? We're going to see a slope that's going up. All right? We're going to see this same acceleration. All right? Our acceleration during our first second was 1/1. Second, we did not accelerate. All right? My acceleration is going to stay flat. Now my acceleration during my next one is going to go up. My acceleration during the next one is going to go down. See it go up again. All right, I'm going to see it go up again. Similar to my position graph. All right? But what acceleration is going to tell us is something totally different. All right? because it's telling us how my rate is changing. And we can draw graphs. All right, and I should have done this first, okay? Should have done this before I did the other. Velocity versus time. So, sorry, I did this backwards. Would have made it a lot simpler. All right? And we're going to work with a, and I should have done this too. I should have worked with a constant velocity first. All right? First year teaching physics in 15 years, so I'm going to make mistakes, y'all. All right? Some things we need to understand on a velocity versus time graph. First of all, velocity, okay, is going to be our vertical component. All right? All right, velocity is going to be our vertical component. Time, obviously, t is going to be horizontal. Our slope is going to equal our acceleration. All right, so our rise over run is going to give us acceleration. All right? Now, when acceleration is constant, all right, it's going to be a straight line. Anytime we have constant acceleration, we're going to have a straight line. All right? And constant velocity. Or sorry, no, not constant velocity. So if I get a line here, what this is telling me is that there's no change in velocity. Okay? So line A here, all right, straight line, no rise or run. This is going to be no acceleration. That's telling me. All right? This is on a time versus velocity graph. Now, if we say this is north, and remember it's a vector, so we have to give it a direction, and this is south. All right? The velocity here is going to be to the north. If I come down to the bottom and do the same thing, I'm still getting no acceleration, no change in velocity. All right, my velocity has not changed, but now I'm going to the south. To the north, to the south. All right? So my velocity is the same, but my direction is different. Okay? Everybody understand that part of it?
Yep.
All right, see, I should have done this first. So here heading to the south. All right?
So what's the middle one? 0.
That's a 0. That's my.
Oh, okay.
Do you need me to color code it?
Happy with me.
I can. I mean, I'm serious. I'm asking. Would it help if I color coded it?
Probably.
Probably. Okay, so let's change my lines here so that you know which one is my graph and which one is not my graph. Don't be sneaking up behind me.
You just have to throw a piece of paper.
I'm crazy. Sneak up behind me like a snake or something. All right. So now I'm moving at constant velocity to the north or to the south. All right. Now, if I have a slope, it's going to tell me a lot too. All right. So in this case, we'll draw a line C here. All right. Line C is going to have a constant acceleration towards what? To the north. Okay?
And beyond.
All right, so now I have constant acceleration to the north. All right? Now, what about crosses the line but is still accelerating? All right? Obviously, all right? But because I start out down here, what is happening to my acceleration here? Is it positive or negative?
Negative.
I'm having negative acceleration to the south. All right? And then I'm going to have what? I'm speeding up going to the north. All right? Going here, and at this point, everything stops and accelerates to the north. All right? So there's a 0 point here, and acceleration changes directions. South to north. This would be like doing what? I'm running a race and I have to get to a point and turn around and go back the other direction. All right? I'm running a shuttle race. Okay? All right? So my acceleration changes direction here. All right? Now, boop. All right? Tells me what's going on. I'm slowing down, aren't I? All right? And I reach a point, and then I do what? Stop. Everything stopped when I got here. When this person got to this point, or this object got to this point, it stopped. All right? What does this tell me about my acceleration?
It's going down.
It's going down. I'm slowing down. Okay? Which direction am I moving?
North.
I'm moving north.
If you were, if it's acceleration, that means it wouldn't. Oh wait, your acceleration thing. Okay.
Is slowing down. I'm getting slower and slower and slower.
It's not how much you're accelerating.
Okay.
It's
So this is where this is running. This is you break free. You broke free on a long run, and then you start high stepping it into the end zone. All right. When you high step it into the end zone, you cross the line and stop. Right? Everybody's gone the other way. They followed the fake. You're running down the field, and all of a sudden you realize, hey, I can just cruise. Okay? And they just run nice and slow and high step it into the end zone. Actually, it looked like it'd be fast first, and then it'd go back the other direction. But increasing their acceleration as they come to the finish line because they're so far ahead. All right? Never do that, by the way.
how many times has that bit someone in?
That has bit a lot of people. That has bit a lot, and I've seen guys do that in football games and get tackled from behind. Never happened to any of my running backs, but
That ever happened?
I've had guys on my defense run people down that decided they were gonna slow walk it into the end zone or do something cool at the end, and
That ever happened in the
So- don't ever slow down at the end, all right? But this would be decreasing acceleration towards the end, Alright, I should have done that first. Okay? Should have done that first. So now I know. Questions about this, and we'll come back to the other two tomorrow with the information that you have that we collected the other day. We're going to plot that data. All right? The second part would have made more sense if I did that first, right?
If I had a fan powering here and then a turbine here which is connected to the crankshaft, well, and so and then actually when these come down, it releases all the built up into the crankshaft area, and then because it's a vacuum, it will never go up because the vacuum it's going to be a fan over here creating a vacuum, and then there's a fan here cooling it, but then there's also a turbine, so it's also power.
Yeah, but if you're releasing this, it's also heating it up. This has to be, if you're releasing the energy that comes out right here into this, it's going to heat it up. You're not going to be able to get enough air through there.
So I can't release it into the... Well, because the idea is that the air pushing through creates it. It's also powering the turbine.
She didn't actually teach us that.
That's kind of what I want. I want as it pushes the air through, it's powering a turbine.
Yeah, exactly. We're doing couch demos.
That's what I mean, that's the supercharger. That's what a supercharger does. But it does cool. That's part of what a supercharger has to do.
It's time for your lunchtime prayer. In the name of the Father, and the Son, and the Holy Spirit. Amen. Blessed the Lord, and these thy gifts which we are about to receive from thy bounty through Christ our Lord. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen. Teachers, would you please release seniors?
When they have front-wheel drive, would the van be elastic so it stretches out when it pulls away, but then it condenses and it's still turning the wheels? Do you get what I'm saying? Yeah. On a front-wheel drive car? Would that work? Like having an extendable converter.
Yeah, bro, listen. You're not going what? He does.
I really don't understand that. Because I'm like, the positioning, like, that's kind of what you have to do on the front wheel. Also, on the idea of, I guess, how on the high torque axle, is that it's an arm is only out on one end, and once it hits the top, it falls down. So it's always on the going up side, never on the coming down side, creating more. So it has a larger surface area on the side that goes up. So it's like goes up, comes down, and then goes back up and comes down. You know what I'm saying? Like this.
I go feel when stuff was on you have what? This is your big back
like that. And so that way this side has nothing, therefore making it quicker, and this side has all this, making it slower, making it spin quicker.
Thank you.
Would that work?
I don't know. Diagram it out.
Alright. So,
as with all things in physics, draw a diagram.
Alright. So the cooling area, the pistons themselves have to be cooled. It's not the air around.
No, the engine block has to be cooled.
Okay. With my design, it's less of an engine block, and it's less of the engine is more a part of the car than a specific system within the car. It's more built into the car, which I think is one reason no one's tried to do it like this, because they always want to make it a singular unit, whereas it could be more efficient if it was less a unit and more a coexisting inhabitant. Because then you could make it interact with other
Interesting
things.
concept, Jonathan. Go lunch. I got a headache. I need a break.
Allows it to interact with everything else.
Teachers, would you please release sophomores for lunch? Freshmen, you're released at the bus. Thank you.
I don't do his class. I hate to fuck up his class. His class is go to hell. He's so boring. I had him 2 years in a row. He was boring. Oh my god. And I had Miss Art last year. I had him for biology and Miss Art last year. Oh my god. I hate this class. Well, next, I have to ASL 1. Oh my god, it's not funny. I've done with my 4 languages. I took Spanish for 3 years. And they didn't have anything else available, so I had to take ASL 1. Where's it? Hi. He gave you your bag? Okay, good. You left it.
Oh, yeah. I went to go back and get it, and then he was walking this way. Yeah,
Okay.
thank you.
We're learning.
We got 3 more minutes left.
My next 2 classes are fun. My next 2 classes are free classes. The what?
What's up, kids?
Well, there is, oh wait, I still cannot handle, the test. Because I'm failing your class. Because I pressed the arrows on the text, which made the F on the test. It's not funny.
How many years have you gone here and taken the test on the computer?
Yeah, but I forgot, obviously.
It's kind of funny.
It's not I'm failing this class.
It is a little bit funny.
I understand that.
Come on, I'm the worst camp person on earth. And even I haven't done that.
I did it like other
When you scroll down, did you guys see the HR budget change before you went down?
What is it?
You ever need panic?
It may not be right now. It's not gonna happen today. But we'll get it. I'll get it.
It will be before homecoming. I will not.
Yeah.
I will not be doing that.
Most important thing.
Run.
91.
What the heck? How did y'all?
Did y'all not cheat, yo?
I did.
I cheated.
I did too.
You said no or yes?
August 28th. What we should have taken 4 weeks today. Yeah, you gotta take 4 days so you can survive. The goal is just take 40 minutes of now. No, the goal is just 80 minutes.
Can I get a picture? Really fast.
Run, hurry. Just got back from lunch. Should have done that already. Do it before you get here.
Oh, I grabbed the wrong binder. Can I go to the bell ring?
No problem.
Start closing some tabs.
You need our promo.
Oh.
Something like that.
Just wait, bro.
Gotta do the business end first. How about? Alright, right in the Devo card. So, answer
Online.
online. Alright. Need to go here. And I need to go here. Alright. Sydney.
Here.
Casey. Emerson. Alex.
Here.
David. Hernandez. He is online temporarily. Let's see. DeWitt is online. George. Ivy. Alright, Anissa. Here. Mark. Hunter. Mark. Here. Kenny. Kenny's online. Sim that.
That was okay.
Straighten out. Alright, take your notebooks back. Y'all's test is going to be Friday. Number one.
Monday.
Physics. Test is Friday. 9-11. Next test, I'll give y'all a study guide tomorrow.
3 days to do it.
I'm Friday. I was sleeping. No, it's this test on this Friday. No, I'm just
Let's do a little review. So I got your notebooks. If you're staring at your Chromebook, I know you're not doing what you're supposed to be doing. I got your notebooks. Let's do a little review. All right, let's see. So the next test will start from where we ended on the last one, which was basically going through our physicist, right? So next one will start with Newton's first law and go through everything we do on Thursday. All right? All right, so what is Newton's first law?
Inertia.
Inertia. What does inertia mean? That resist change in motion. All right? Make sure you make yourself familiar with blank question. Every object continues in a state of rest or of uniform speed in a straight line unless acted upon by an unequal net force. Right? Do what?
Old notes right now?
Yeah, right now we're just going over the old notes. I just want to, you say that's a great fill in the blank question.
What is it?
All right? The law of inertia. All right? Every object continues in a state of rest or of uniform speed. Let's see. In order, let's see, what is a force? What is a force? Simply stated, what is a force?
Any push or pull on an object.
Any push or pull on an object. If my net force is all these,
Total forces.
that's the total forces. All right, in order to have a sum zero force, what is the minimum number of forces I have to have? 2. I have to have at least 2 because if I only have 1, I have force moving in one direction. All right, I'm going to have movement in one direction. A vector.
direction and
Any force or motion that has a what? You were right. It has both size and direction. Okay? A vector has to have a direction. So it has to be to the right, to the left, to the north, to the south. Okay, so vectors always have direction. Scalars just have a what?
speed,
Magnitude and size. Miles per hour, which is what? Speed. What else? Time. Mass. Temperature. Okay? Those are always good. Those are our scalar quantities together. What? I think you got it right, but I couldn't hear you. What do we call it when we add two vector quantities together? Starts with an R. Vector quantities together. What are parallel forces? Take your head down. What are parallel forces? Not necessarily in the same direction, but they're in the same way. So if I have two forces of 5 newtons, force do I have going to the right? 10. If I have 5 newtons of force going to the right and 5 newtons of force going, if I have forces in opposite directions, not opposite directions, in perpendicular directions, what do I have? What can I do to figure out my vectors? That's Pythagorean theorem, yes, but what is the rule that I use? I have perpendicular vectors. What can I draw?
A triangle?
I have 5 newtons in that direction and 5 newtons in that direction, right? And then I have I can draw my parallelogram, and then I can draw my triangle, and then I can use what? Squared equals c squared, and c squared is my what? What do we call this part? Hypotenuse. Good. That's called the parallelogram rule. Parallelogram. Parallelogram rule. All right? For perpendicular forces. All right? Remember, we can use that same rule to figure out forces. Remember our gorilla hanging on the rope? Okay? Remember the gorilla hanging on the rope? There's my gorilla. He's a gorilla. Right? He has a force down. Right? Right? And then we can draw our parallelogram. And now we know how much force, okay? And that's where we can figure out where there's more force. All right? What does this symbol mean?
Some. Everything total.
All the forces added up. If I have a...
Oh, he said what is...
If it is sum forces equals 0, what are we at? Equilibrium. All right, if something's at equilibrium, what's it doing?
Not changing position.
It's not changing position. Oh, it can change position. It's not changing Or what? It may be also what?
Um,
It can be sitting still, or it can be traveling at a constant velocity. The old Star Trek, I know you've seen clips probably because they use them in commercials all the time and everything else, and people like make fun of them, and the engineers calling down from the engines are overheating, we can't continue this speed. And what Kurt should have said is just shut the engines off, because we're in deep space and we're not being acted on by an unequal force, and we'll maintain this speed. All you got to do is shut the engines down.
The engine shut off and it slowed down.
Yeah, that's the engine shut off or something. No, you don't slow down. Okay, you can't increase your velocity any, and even at warp speed. Well, guess what? In the bubble, there's still no friction. You know, even in the bubble of there's no. You should just continue.
no.
All right, at speed. Let's see. What we call the support force when something is supported by something else. What is that called?
Normal force?
Normal force.
Oh, I do.
All right. What is its relationship to the supporting structure?
It's always support perpendicular.
It's always perpendicular to the supporting. It doesn't matter what it is. All right. So if it's here, or if it's my gorilla hanging on the rope, perpendicular. Here, it's still perpendicular. All right. My supporting force is still perpendicular. Even though the force of gravity is hanging on the rope and the rope is not breaking, the supporting force is perpendicular. All right? Even though this is going to equal out, and the supporting force is going to be perpendicular here because he's holding the rope and the force, the supported structure. All right? We call that the normal force. What kind of force is the normal force? It is perpendicular, but what type of force is it?
Contact.
What's another contact force? If I try to slide something across the disc, friction is another one. Okay? What is equilibrium? We already said that, didn't we? We already did equilibrium. What happens to equilibrium through space when we're in a moving vehicle? I'm in a car. Equilibrium. I'm moving at a constant velocity with the car. So relative to the car, I'm at equilibrium. Relative to everything around it, position, doing. It's changing, and if I speed up or slow down, my equilibrium is changing to the outside observer, all right? Let's see. What is my formula for speed?
Distance divided by time.
Divided by time. And remember, we read that dash as per. So if I'm going 45 miles per 1 hour, okay, it's 45 miles per hour. They try to kill me every morning coming into work. One of these days, y'all are going to come in, you're going to go, all right? How do we get instantaneous speed?
Speedometer.
A speedometer. That's our speedometer speed. And here's the thing about, understand something about trying to get instantaneous anything. Instantaneous equals what as far as the amount of time? So if I'm looking at a graph, all right, I can estimate my speed, okay? I can get my average is going to be my rise over my run. Right? To get an instantaneous speed, doing it, especially if speed is changing and I'm accelerating, and we'll get into that later, we have to break this down into smaller. No, we can't ever really get it to zero, so we can't ever really get a true instantaneous speed. Best bet is a speedometer. We can get really close, okay? You can use calculus and close, but we can never really get a perfect instantaneous speed. Get really close, just within millions of speeds. Very difficult math problem. Are speed and velocity the same thing?
No.
Velocity is speed. Velocity has direction, speed does not. And I don't know if I told y'all this or not. Speed is the absolute value of velocity. All right? Speed will always be your absolute value of velocity. All right? And we're going to do a little graphing today. All right? Since direction can change, all right, on a velocity graph, all right, it has obviously changed. But my speed is still going to be the absolute value of my rise over my run. Acceleration that we'll get to later. But even if my velocity is making a negative line in here, my speed is still going to be my rise over my run. Will always equal the absolute value of velocity. So write that down. Because even if I change directions, that'll change my velocity. Because it's a vector, right? If I change, traveling through space doesn't change. Right, in Talladega, they don't even lift. They don't even come off the gas, do they? You get at Talladega and they just, like, it's a huge track. They just put the speed doesn't really change. The vector changes though, okay, because the direction changes. Right, so there's a change in acceleration, but the speed itself doesn't change. So the actual vector will change, all right? But the speed will be the absolute value of that velocity, all right? Even though the vector and the velocity will change because the direction changes. Do a little graphing today. We haven't done much graphing in here to understand where all of this fits in. All right? This is going to be a time. All right? Time is always going to be t. Position can be x or y. Okay, my position can be X or Y, or it can be, actually, it can be S.
This is our new notes, right?
If it's displacement. Yeah, this is new. All right? Now, what's different about this graph than most graphs you see in math books? What's it missing?
The Y and...
There's no negative value over here, is there? Here's Y. Time. All right, we can't time travel backwards. Yet. No one showed up at Stephen Hawking's party. So You know, in the future, if all of a sudden there's a thing that comes out and says, so, you know, people who were at Stephen Hawking's party will know that people figured out, right now we don't know how to go backwards in time. So time is always positive. That tells us that T is going to be our horizontal axis, okay? Time is our horizontal axis. Horizontal axis, right? The origin is the point where all values, I can't spell today. That's going to be our 0 point. Now, our position is going to have a positive and a negative. So whether position is going positive or negative. So we can name those whatever we want to, okay? It can be north and south, east and west, up and down, all right? And usually the only time we use Y is when we use vertical displacement. We usually only use Y and vertical and S if we're using displacement values. All right, but X will give us that too. All right, so X is our position. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 1, 2, 3, 4, 5, 6, 7, 36, negative 7, negative 8, negative 9, negative 10, negative 12, negative 13. All right? Now, we still work in positive and negative. All right? And we can give those, again, it depends on what we want to be positive. If we want up to be positive, and we usually do, up will be our positive value. If we want down to be negative, it will be our negative value. Therefore, think about something. Gravity is always going to be a negative force. All right? Yes? Yeah. All right? Just something to throw out there to think about later. Gravity is always going to be a negative. All right? And we can do these with forces as well. All right? So when we're talking about movement through steady pace here, trying to make it straight here. All right, maybe I need to color code this a little bit. Make it a little easier to see. So each of our positions here at each second. We can make an arrow here. Right, because we know it's moving in a positive direction. All right? So we can get a lot of information out of this, and we'll say this is 1 second, and this is 1. So at position 1 right here, what can we tell about this graph right here? It is 1 second, all right? And it is moving 1 meter. What do we know? We can determine speed by that. Okay, so how do we get the speed out of that?
Distance divided by time.
Okay, it is the distance divided by time. We can also understand it by looking at the slope here. Okay? So it is going to equal our rise over the run. Right? And our rise is 1 meter over meter per second. All right? We're going to be moving at 1 meter per second. Now, because it's a straight line, what does that tell me? What does it tell me that it's moving in a straight line? Is it changing?
No.
No, because now, right? 2 seconds. It has moved 2 meters. Now and we're going to get 1 meter per 1 second. All right? So we know that our speed now is consistent. Now, since it is moving upward, and we will name this direction, what else can I figure out now? This can be a what? It can now be a vector, because my vector quantity, okay, my per second north. All right, so now I just put an arrow over that. And I've got my vector velocity. Now I know the velocity that this thing is moving. All right? Now, is this line actually telling me where it's going on a map?
No.
No. Through the state of Georgia up here, right? And it kind of goes like that, right? And we were going from here to here, all right? And the road's like this. We're going to go around Atlanta. This vector that we're talking about here is only north, okay? And here we would only be talking about the northern move. Figured out it's 163 miles straight away, and it's 193 on the highway, but it's only probably 70 segment of the motion here. Okay, we will be breaking this down into our north displacement. All right, because now we're looking at displacement over time. All right, everybody with me so far? Confused. Okay. If I have motion in more than one vector, don't try to do it all on one graph. Make another graph. East and west, and we would make east our positive and west our negative. All right? Yes. Yeah. And if we were to do our 63 miles of displacement, all right? I'm not exactly sure what it would be. It may be more like 90 here and 63 here. Not exactly sure. I'd have to plot it out on a map. But if we get more than one direction, don't try to do it all on one graph. Make a separate graph. Always break things down as much as you can. All right? Always break it down as much as you can. All right, so I'm going to give you some values, and you're going to make a graph. All right? So make your little graph. These are the values I'm going to give you. All right, this is my x value. Sorry, this is my t value. And this is my, I'm going to make this an x value so that it's horizontal. So 0, 0. All right? All right, so make your little graph. do a little practice here. All right, make the first one easy. This is also a good practice in determining what you want to make your values. I do on my T. And we'll say this is meters, seconds. It's not always in seconds, but usually we use seconds. All right? Just a little practice. We're going to practice this again. Different types of forces, different types of vectors. Give you a second to play with that. And eventually we'll be actually moving things down the concourse over here. Playing with Hot Wheels. We will play with Hot Wheels. All right? All right, so how'd you do? How'd you do? Let's see. What's the first thing I need to do is remember that, first of all, I only need half of the graph. I don't need anything over here. This doesn't exist right here. Did you make your X value here? Now, 3, 4. Now, to make a good graph, do I want to come over here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15? Do I want to do that? No. Why? It's too much. It's too much. It makes it sloppy. Okay? Do I want to do things really small over here? No. Make 5, 10, 15, 20. Flat graph that's too flat or one that's has too much trajectory in it. All right? And I can now use this to compare things. So, at 1 second, obviously started at the origin, right? At 1 second, how many meters did it move? 5. So, should have a point there. At 2 seconds, how many meters did it move? 10. It had been 10 meters at 2 seconds. At 3 seconds, 15, right? If you can't draw a straight line. All right? Now, I can use that. What is my velocity? Or, yeah, let's see. We'll make this rise over the run. So my rise is what? 5 meters, 1 second. Okay, so 5 meters per second. I can say my speed. If I were to give this a direction, okay, let's say the direction is to the right. All right, I could make this a vector, right. Okay? Pretty easy on that one. Okay, that one's easy. I'm going to keep using 0, 1, 2, 3, 4. This time, we're going to go -2, positive, get to an easily divisible number here, 0. 12. All right?
Good. Everybody's great. Thanks.
3 seconds did it go? 3, 4 seconds. 5, 10, 15, 20, 5, 10, 15, 20. All right, so where's my starting point on this graph?
0.
About right there, isn't it? All right, this was my first one. All right. Now my second one, let's see, 5, 10, 15, 20. 1, 2, 3, 0, 2. Where am I at my first second? So 1 second, what? Positive 2. So I'm right in here. Second, where am I?
6.
Positive 6. Third second, where am I? Positive 10. Fourth second, where am I? 12. All right, things that are different about this graph. All right. Does it make a straight line? No, it doesn't make a straight line, does it? Okay, so I can get my average speed and I can get what we call an instantaneous or an estimated instantaneous speed. All right? So here, pick that up tomorrow. All right? Practice graphing. You go ahead. Come on, Crip.
That's tough.
I'm blood, but I'm cripping, you feel me?
You good, Quiz?
Huh? Yeah.
Not bad.
Yeah. I'm sitting in a big family.
Tell me what you need from me. You see I've been abused. Okay, tell me what you need from me. You say
I get verbally and mentally abused by my parents.
you got gum? Yeah. Can I get some gum? I do it every day solo. Not more than that. No! You can't hit me.
In 7th period, I will be watching the England versus Denmark game.
Someone snatched my crutch at lunch. I'm still on.
That's tough.
What's up, kids?
What? Y'all have to see what's inappropriate is.
Dang it.
All right, for a couple of days, Dylan,
I saw you practicing this film at halftime.
be patient when you get
You practicing this film. Then we did that shit in the game like, oh. How you just hit that? It doesn't even make it halfway before the ball. It doesn't even make it over the day before Instagram.
Just stop. All right, so Kenyon, Sincere, Connor, Cole. Is Cole Ego?
Yes.
Okay.
It was like
Cole Crawford. Gavin. Vanessa.
Here.
Austin.
it was going in this silent sentence.
Here.
Mia.
Here.
Here.
Reed. Lowry.
Online.
I didn't know who she was until she came into the club.
Oh,
That's
Nugent.
Georgia chemistry, bro?
wow.
Dad and brother got for all.
Dang.
Jeremy.
Fast.
That's who it was.
What?
They were talking about.
Let's see. Solo. Albert.
here.
Who was saying that?
Pierre.
Oh yeah.
Oh.
All right. Gotta send that.
Great.
Go back to Newton's first law.
I actually haven't.
All right, been out 3 days. We're going to review. Next CP physics test is Friday.
This one?
Yes.
Since you're done.
Yes, sir. Test me up.
I didn't know if I got the right one. Oh, I did.
I will give y'all a study guide tomorrow.
Oh, you said okay. Tomorrow.
Yes. I'll give y'all a study guide tomorrow. It will be a physical piece of paper, and you will have to write your answers on it. Yeah. Y'all didn't bother to change. Y'all didn't.
Still on that.
You know, come on, man. They didn't change the picture.
You need to change that one. Don't even bother to change the.
I didn't even draw a picture.
I mean, man, come on. So yeah, it will be a physical piece of paper, and you will have to write on it. I know that's tough. All right, what is Newton's first law called? Law of inertia. What does it say?
I don't remember.
The object.
Continuous at rest or in uniform speed in a straight line unless
It was gonna fall.
Alright, like you going at 4.
Good. Now, this is a great fill-in-the-blank question. Every object continues in a state of rest or of uniform speed in a straight line unless acted upon by an unequal net force. That is a great fill-in-the-blank question. All right? Stated more simply, what does it say? Look at your notes. I gave this to you. I know I wrote this before.
You said what? You said what?
Well, that's what inertia is, and we'll get to that in a second. But stated more simply, what does Newton's law say?
An object at rest remains at rest.
An object at rest remains at rest. And
Object in motion will remain in motion.
the object in motion remains in motion unless good. Let's act on by unequal outside force. All right. What is the definition of inertia?
Property of object to resist change.
Good. Property of objects to resist changes in motion. What is force?
A push and pull.
So push or a pull. What is net force?
The sum of all forces.
Sum of all forces. Combination of all the forces on an object. In order to, let's see, yeah, I don't want to get to that yet. What causes net changes? How do we get a change in position or a change in motion or movement? We have to have what? We have to have what kind of external force? Equal or unequal?
Unequal.
Unequal. In order for a object to remain at rest or in what we will call equilibrium, how many forces do we have to have? At least how many? Four. Like to have at least two. Alright? Because if we've got more than one, if we've only got one, then we've only got push in one direction. Alright? What is a vector?
Any force with both sides and direction.
Good. It has size and direction, or magnitude and direction. What is a scalar? Only has size. What are some examples of scalar quantities?
Mass, temperature, distance, and speed.
Mass, time, temperature, density, length. Okay, anything that just has a size, right? What do we call it when we add two vector quantities? What do we get? What is it called? R word. Resultant. Okay? Resultant is when we add up all the possible vectors. Alright? What are parallel forces? They're forces that are parallel or on the same what?
Plane.
Same plane. All right, parallel forces are going to be in the same plane. Are they necessarily in the same direction?
No.
No, they can be in different directions. All right, so if I have an object, and let's say I have this, I'll draw it up here. I have an object, and I have 5 newtons of force in that direction and 5 newtons of force in that direction. These forces are equal. All right. How many newtons of force do I have going to the right? 10. So I can just add my newtons up. Okay. I can just add my forces up. What if I have 5 newtons going back in the other direction? 5 going to the right, 5 going to the left. What's my net force now? 0. Okay? What if I add 5 back over here, and now I've got 5 newtons to the right plus 5 newtons to the left, right? 5 newtons to the left. What is my total force here? 5 newtons to the right. Okay? So parallel forces are in the same plane. All right? But they may not be in the same direction. What happens when I have forces that are not in the same direction? What can I do to figure it out? Okay? What is that rule called? So remember my box? I have my box right here, sitting on the ice. I have somebody pushing it with 5 newtons to the right. And I have somebody else pushing it with 5 newtons to the, let's call that up. Okay. What can I do now? I can do my Pythagorean theorem. What's that rule called? There's actually a name of the rule. Starts with a P. I know I gave you the name of this rule.
Pythagorean theorem, whatever it's called.
Pythagorean theorem, that's what we're going to get to, yes. But there's a rule for this. Huh?
That's a good question. Paradox.
It should be right there. It should be right there in your notes.
Parallel forces.
Parallelogram rule. This is my parallelogram rule.
Good job with putting me on.
Parallelogram. All right. Rule. And this is where I can take my forces and I can go, I have 5 newtons in this direction. All right. I have 5 newtons in this direction. All right. Now I draw my parallelogram. I don't know why I have such a hard time saying that rule word. All right. And I can find out the direction of my force, of my net forces, by finding out what my hypotenuse is, right?
Yes, sir.
Because if this is side A and that's B, A squared plus B squared equals C squared.
Yeah.
All right? So if I have 5 newtons here, A squared is 25 plus 25 equals C squared. 50 equals C squared. Take the square root of both sides. And square root of 50 is, what was the square root of 50?
It's like 7.1 or 7.2.
It's 7 point something.
7.61.
It's like 7.
No, it's like said, yeah. You're right.
It's like 7.15. 7.6.
50 square root 7.07. So 7.07 would be my forces in that direction. Okay? So that's my parallelogram rule where I can use my Pythagorean theorem. All right? If I do give you one of those on the test, okay, I'll try to, and I will give you one of those on the test. I'll try to keep the numbers fairly simple for you, okay? I'll try to keep the numbers fairly simple. I don't want the math to be the stumbling block, all right? So know how to use that parallelogram rule. Remember, we can use this for the hanging gorilla too. Remember the gorilla hanging from the rope? All right? And we can figure out which side has the greater force by using our parallelogram rule. All right? Gorilla's hanging from the rope. Short side's going to be the one that has the greater slope and therefore the greater force vector. All right? Let's see. What does this symbol mean? Nope. Sigma, which means what?
Equal.
Sum. All right?
Equal
That means our sum. It doesn't mean equal, okay, or equilibrium. That's our sigma. Sigma is always going to be the sum of our forces. All right? What does the F equal? Forces. If I have sum of the forces equals 0, then I've got what?
0 net force.
I've got 0 net force, but I've also got what term? Equilibrium. I can't spell it. I don't know what it is. I always struggle with spelling, but for some reason today I'm really struggling. Okay? That means my net force is 0. All right? That's always going to mean my net force equals 0. All right? Can an object be moving at equilibrium?
No.
Yeah. No.
No.
Yeah.
Yeah, why?
I don't know.
Wow.
An object can move at equilibrium if the force is because of inertia.
Right, because of inertia.
Yeah.
Okay? Now, that brings us back to what is inertia? Okay, what is our definition? What is our working? We talked about what is it though? When an object possesses inertia, what does that mean?
It's its property to resist change in its motion.
Good. That is its property of objects to resist change in motion. That is not the law of inertia. That's the definition of inertia. All right? This is, y'all ever watch Star Trek? Okay, I know Connor watches Star Trek.
Yeah.
The old ones too.
Very, very old ones.
Yeah, those are the best. Those are the best. This is why when the engineering room is calling up and saying, "Gas, Captain, I don't think we can keep her going. The engine, the dilithium crystals are melting down and I just can't keep the speed up." Well, Captain should have just said what? Well, shut them down. We're already moving this fast through deep space. And unless an unequal net force works on us, do we actually need the engines? No. Because once you get up to speed in deep space, what can you do? You just keep going, man.
There's nothing to stop.
There's nothing to stop you. There's no friction. There's no gravity. Or gravity is negligible. So you just keep going. So, you know, Captain Kirk should have just called down and said, "Well, shut them down. We'll keep going this fast. We're not going to change."
They're not that smart.
All right? Not going to change. I just ruined I'm going to ruin your childhood so many times when you learn physics. It's like, oh no! You mean they didn't really have to do that in Star Wars? Nope.
Star Wars?
Really didn't. Okay. Really didn't have to do all that stuff in Star Wars. Let's see. If we have a net unequal force, what can we produce? What do we produce? Yes. What? Motion. Thank you.
Yeah.
Okay. Motion is produced by motion is produced by an unequal net force. All right. That's when we're going to get motion and we're going to get acceleration. We'll talk about what acceleration is later. All right. Remember, net force is a combination of all my forces. How many forces do I have to have for something to remain in equilibrium? Minimum of what? 2. I have to have a minimum of 2. So remember, for my box to remain in equilibrium here, sitting on the table, all right, I've obviously got what? Gravity going down, right? And I've got a force going up that's equal to that. And if it's not equal, what would happen? It would either crash through, or if the force going up was greater, it'd do what? It'd fly up in the air. All right? So I've got to have a minimum of 2 forces to get my net force to 0. All right? If I have a push from this side and it's still not moving, what's my force from this direction? I'm pushing over here with 5 newtons, but it's not going anywhere.
It has to be 5 newtons.
It has to be 5 newtons back, right?
Yes.
And that force is going to be what?
Equal.
It's going to be equal. Now we're at net 0. Well, we hadn't really gotten to that yet. We'll come back to that thought in a moment. All right? Make sure I hadn't missed anything. All right, what's a vector? It has a what? Has a direction. Vectors have a direction and a magnitude or size. All right? Vectors always have a magnitude and a size. What's a scalar? Just a size. What are some examples of scalars? Mass, temperature, time, length. Good. Let's see. Did we do the parallelogram rule?
Yes.
Okay. Just making sure we got everything down. Talked about the gorilla hanging on the rope. Sum forces equal 0, right? Did we do sum forces? Yeah, we did that. All right. When I have what is my support? What's another name for a support force? It's a normal force. All right? Normal force is always what to the supporting structure? My normal force is always what? What relationship does it have to my supporting structure?
They're equal, right?
They're not necessarily equal. What is it? Do what? Perpendicular, okay? Anytime I have a support force or normal force, it is always going to be perpendicular to whatever it is supporting. All right? So here, it is perpendicular to gravity, right? What if my slope, what if I'm sitting it on an angle, an inclined plane? Where is my support force? Where's my normal force? It's what? What is it to my supporting structure? Here's my supporting structure, so it's going to be perpendicular. Perpendicular means like a what, Connor? Connor, you're trying to pin somebody. Why do I yell get perpendicular? Because I want you to be like a
good wrestler.
What do I always say? Like a what? Like a T. Okay, perpendicular means like a T. So that's okay. See, he should know that. Okay, that means
I don't get like a T. I'm a freaking cradle. I don't do none of that.
Oh yeah, you're still perpendicular, believe it or not. Your force is. All right, so my force is going to be perpendicular to my support. All right, my force is going to be perpendicular. My normal force is perpendicular. Even though the gravity is in this direction. All right, if the force of gravity is greater than my support force here and my friction force going down, what's going to happen? My box is going to slide, right? All right. So if this force is greater than a force of friction going back in the opposite direction, I end up with a sliding box. All right. If my support force is less than my gravity here, then I'm going to break my inclined plane. All right. Lots of things going into that, and we'll discuss them later. But my support force is always perpendicular. Even with my hanging gorilla. Remember the hanging gorilla? All right, Coach Anderson wants a gorilla for a pet. All right, here's my gorilla. He's hanging on right here. Here's my gorilla. All right. The support force is actually going to be perpendicular, right, to the gravity, and gravity's pulling down. My support force is actually going to be right there. All right, so that's going to be my supporting force, and it will be actually straight up and down and perpendicular to the ground. All right, now there's also force here, right? And there's also force here, and we worked on that with our parallelogram rule as well. All right. So that's our normal force. What creates the normal force? Something you learned about in chemistry. Starts with a V. Something you learned about in chemistry. What do we call those forces?
Van Gogh.
No, not Van Gogh. What is it about the atoms in the table that keep me from going through? Van der Waals forces. Good. Excellent.
Did not learn that.
No, we probably I didn't learn.
No, so we not learned.
You didn't learn that.
Y'all didn't learn that in chemistry? Hey, you're going to learn it in physics. It's coming. It's farther down the line, but we'll learn about Van der Waals forces. All right. Let's see. What is the force that causes things that are moving through space to slow down on Earth? If I'm pushing something across the table, what force am I going against? Friction. Okay, remember there's friction. All right? Friction is always parallel to the surface. Okay, friction is always a force parallel to the surface. We don't need that yet. But there's also that frictional force, right? Let's see. What is motion defined as? Come on, this is easy.
I have no idea. I need help. I feel like it's wrong.
It's a change in what?
Movement.
Position. It's just any change in position. God, see, y'all make stuff so hard. Make it easy. It's just a change in position. Anytime I have a change in position, I have motion. All right? What do we like to know about motion? What do we like to know? How fast something's going. How do we figure out the average speed of an object?
You multiply the distance, you divide the distance and the time.
Good. Which one do you divide by which?
You divide time, distance by time.
Distance by time, okay? Average speed is just distance traveled divided by time. So when we write down that a car is going 45 miles an hour, all right, what we're saying is that 45 miles per decimal or a fraction. All right, that's what that little line there means, okay, per hour. All right, so 45 miles per hour. And that's how that reads. So speed is just a fraction. All right, we just have to know how far you've gone over what amount of time. So if I have something that's gone 8 miles or 8 kilometers, let's get used to using kilometers. Its movement is 8 kilometers, all right, in 20 minutes. How many kilometers is it going per minute?
What does it say?
8 kilometers in 20 minutes. So how do I write it? 8K over 20 minutes.
1 every 2.5 minutes.
All right. So how many? How do I do this?
Kilometer every 2.
8 divided by 20 equals 0.4 kilometers per minute. Could I do that for seconds? Could I do the same thing? I just have to change my minutes to seconds, right? Divided by 60. So I can change and I can figure out exactly how many kilometers it's going per second. All right? Won't worry about that at this point. All right? What is instantaneous speed? What's the best way to get instantaneous speed? Speedometer. Remember, it's difficult to get instant, and we can get really, really close on instantaneous speed, but we're never going to get it exactly right, right? Because speed does change every second, right? Even if you think you're being pretty consistent at running it or driving at 45 miles an hour, there are little changes and little shifts that take place, every second. But exact instantaneous speed is still going to be just an estimate. All right, so the best thing that we can use there is the speedometer speed. It's a very difficult math problem. Let's see. What is velocity? It means I have speed and direction. All right, are velocity and speed the same thing? No. All right, velocity is a vector quantity, speed is not. I don't think I gave you this. Okay, speed will always equal the absolute value of velocity. All right? Speed will always equal the absolute value of velocity. Because speed is a scalar. All right? Speed is a scalar. All right, that should get us caught up. Okay? That should get us caught up. Now, what I want to do today is I just want to play with graphs a little bit. All right? I want to kind of start with some special graphs that you're going to need to know how to do. All right, the first one that we're going to do is a position time graph. Now, position versus time graph is going to look a little bit different. All right? First of all, it's only going to have 2 quadrants. So it's going to have 2 hemiquadrants. And here's why. Your horizontal axis is going to be time. So we're always going to put time on the horizontal axis. All right, so time's going to be our horizontal axis. Our vertical axis is going to be position. This is going to make your graph a little bit different than the ones you do in your math class. All right, time's always going to be on my vertical, or sorry, my horizontal. My position can be X, it can be Y, it can be displacement, all right? So that's going to be on my vertical axis. All right, so X now becomes my vertical axis and T is my horizontal axis. Whereas in math class you use, this is always X, this is always Y, right? All right? And here in physics, time is always here. All right? Time is always on that horizontal axis. Position is always on my vertical axis. All right? Don't mess that up. That's a common mistake for first year physics students. They'll put time on the vertical axis and have negative. Now, there's no negative side to time. We don't have negative time. At least not yet anyway. Nobody has traveled back in time yet. All right, we can't do that. That we know of. No one has showed up to Stephen Hawking's party, his time traveler party yet. Nobody showed up. Now, if one of these days the papers, you read in the paper that, the dozen people that were at Stephen Hawking's time traveler party have gone back to the future, then we'll know that at some point in the future, we did actually have time travel in an alternate universe. Just say. All right? So right now, there is no negative side. So when you draw a time versus position graph, don't draw this leg. All right? And that'll help you to remember that time always goes here. Because if you draw this leg, you're going to screw up. You're going to put time here and position here, and it's going to mess the whole thing up. All right? So when you do a time versus position graph, or a time versus velocity graph, or a time versus acceleration graph, or any type of graph where there is time is horizontal, it only goes in one direction. All right? So remember that. There's always an origin point, okay? Origin is where all values equal 0. And that's my origin right there. All values equal 0. All right, so let's put some time values up here. 1, 2, 3, 4, 5, 6 seconds. 1, 2, 3, 4, 5 meters. 1, 2, 3, 4, 5 meters. All right. And this would be -5. This would be 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. So that stays the same as your mathematics or your math. Okay, up is positive, down is negative. All right. Now let's put some positions on here. Let's go 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 5, 5. Okay. And I should have a pretty straight line here for hand-drawn graph. Not bad. Now, we can figure out a lot of stuff by this. All right, we can figure out a lot of things. First of all, it's a straight line. All right, it's a straight line. A straight line tells me that velocity is not changing. All right, it's telling me that my velocity is not changing. I can also get my velocity here, okay, or my speed, by knowing that speed is always going to be equal to my rise over the run, which is the same thing as saying distance divided by time. All right? So I can get my speed simply by knowing the rise over the run. So in this case, I can look at any point along here, and I can go 1 meter, okay, it has moved 1 meter over 1 second, and therefore I've got 1 meter per second. All right? 1 meter per second. It will also equal my average speed here. All right? So if I've got the same formula here, 5 meters, and it has gone 5 meters in 5 seconds, all right, I can do my division here, and I still get 1 meter per second. All right? So I can get my average speed there. I can get my average velocity if I give it a direction. If I say this direction is north, I can make it into a vector. I can say that it is 1 meter per second. Put a line over it to indicate that it is a vector, and then say which direction, to the north. All right? Now I have a vector. All right? And now I draw an arrow. All right? Instead of a line. That way I know what I'm dealing with. I know I'm dealing with a vector. All right? Arrows are vectors. Lines are scalars. All right, everybody kind of got the general gist of time position graphs. Now, let's practice. And we'll do this from time to time. We'll just do graphing practice because a lot of what we're doing here is graph. I'm going to draw a lot of graphs over the next, I don't know how many weeks we got left. I'll tell you what, I'm going to give you coordinates, okay? Let's see, this is going to be my time. This is going to be my position, all right? All right? Make me a time versus position graph for that. For those coordinates. Make me a time versus position graph. And use the skills that you just learned. Starting with making the graph right. Really simple, it should be really easy. Shouldn't take but a second. And if your distances between your things are not exactly right, it's okay, I understand. It's a hand-drawn graph. I will supply you with graph paper for these types of questions on test. All right? You will have to show your work. Yes, I can intuitively do them myself. I can intuitively look at that right there and tell you a whole lot about it without graphing it. That's not the skill level. The skill is knowing how to work it out for when you have something a little more complex. That's, I mean, you can look at that right there and it's pretty easy. Without even graphing. All right, everybody got that done? So, first of all, what does my graph look like? All right? What's on my vertical component?
X.
This is my X, right? This is my X position. All right? What is on my horizontal axis?
T.
Time. Does it go back here?
No.
Do I even draw it?
No.
No, don't even draw it. So that's going to be my time. All right? Now, next comes a skill of graphing when we make graph that you kind of need to, you kind of got to feel this out a little bit, and it comes with experience. I need to make my values in a way that they make sense. Okay? So I'm working in seconds, so I'm going to make my seconds about that far apart. That was a little far. I'm going to make it right there. And then 4 seconds. Is that all the seconds I had? Yeah, 4 seconds. All right? So I got 4 seconds. Now, do I want to draw, what have I got, 20 little lines over here? No, I don't want to do that. Okay? But I want to make my graph so that my initial graph especially, and this is going to come in when we start comparing velocities and vectors and force vectors. My initial one, the one I want to compare to, I want to try to get that good line that is very readable. So I'm going to make this one, I'm going to make 1 second and 5 meters about the same. Okay? Because I know that's the distance I'm dealing with. And those are not quite the same. Not quite the same, but they're close enough for a hand-drawn one here. And I'm going to make that 5 meters, 10 meters, 15 meters, 20 meters. All right? There's 1, 2, 3, 4. All right? Now, my first is what? 0, 0, right? So my object starts at 0, 0. At 1 second, it's at what? 5 meters. At 2 seconds, it's at 10 meters. At 3 seconds, it's at 15 meters. At 4 seconds, it's at 20 meters. So again, I've pretty much made me a straight line here, right? Later on, we'll talk about that's constant motion. Okay, that's uniform motion when I have a straight line. We'll deal with non-uniform motion later. But I know I'm getting straight lines, so I've got uniform motion here throughout. Now, if I want to know what the speed is, all I have to do is take what? Rise over the run. So I can do this anywhere on this graph. All right, I can ask you what the speed was between 2 seconds and 4 seconds, and it will still work out. Okay, but we're just going to go here. We're going to say we'll take the whole thing. We'll take the average here. All right, we went 20 meters in 4 seconds, and that works out to what? 5 meters per second. Sorry, 5 meters per second. And that'll work out anywhere I do along this line. It's always going to be rise over run. Very easy to take care of. I know that I'm moving in the positive direction. If I want to make this a vector, what have I got to do? I've got to name my x to the north, okay? All I've got to do now is give my x a name. Then I can say x is to the north. All right? You only use y really when you do vertical. That's
It's always the deep ending, so it's always the ice.
you really only use Y on your vertical component when you're talking about vertical. And that'll come in when we do gravity stuff later. And you'll see why we use Y and X in different times.
Like, I ain't never nobody can do that word.
Y'all have a great day. Stay out of trouble. Don't do anything stupid.
Falling asleep all weekend, stupid.
Yeah.
That's exactly what I did.
That's not healthy.
Not bad.
Rest is healthy. Sleeping all the time is not.
I mean, rest is rest.
Rest is recovery. Sometimes you need a lot of rest. Sometimes you don't need any rest. Stinks. It really is not. It's kind of stinky and smelly.
Look at what's in it. Get too much of it on, you use it too much, you're good.
Probably gives you cancer. Hey.
So tell about the game, like the theme for Friday's game.
I watched them warm up. I went, these guys y'all play good. Good disciplined football.
You guys just play good on Friday, Dylan.
Huh?
Y'all play really good on Friday. Like, I yell at y'all, and I was not yelling back. I was very impressed. That was real good. I used to yell at y'all like crazy. Like, I still yell, but like I wasn't like yelling something loud. Hal, can you get a
Wait. It's so fun.
That's not the
Mercedes, enough is enough. Enough is enough, Mercedes.
Let Austin sit in peace.
And I'm getting tired of it.
Like, let Austin sit in peace.
I'm getting tired of it. I'm gonna be honest with you.
What do you live in? How is stuff hunting?
I was just trying to live my life.
You don't even eat it. I already wiped it on the desk.
You eat them or do you sell
I saw my Brando Buddy P meal.
You just made me a hat, a jacket out of I would cry.
No. Brando Buddy P meal. I missed him so.
They'll carry over.
You just threw your glasses.
I'm just always wanted to just like knock the snot out of students.
I
Never had the opportunity.
Hey, Coach, I'll volunteer.
What?
Coach, I'll volunteer.
We have to canyon this one is one that's a
Not for students.
Y'all are killing me.
Hurry up.
Not for this school.
Out of all the students that need it.
Coach, I can take it.
I'll pretend we got a problem.
Brown, where are you going?
So I don't think you can.
I'll say something.
I've had so many students over the years that really just deserved it. And it's like, you know,
Coach, I deserve it.
the problem with you is your mama never slapped you in the neck when you needed it.
She has multiple times.
Not yours, though.
I should go to child services.
Not hard enough.
It's so funny.
It gets Mo in the week on.
All right, let's see here. All right, y'all bear with me while I do this. I gotta get all my,
Yeah, your car did it for you.
so give me a second. All right, let's see. Natalie.
Because you wrecked your car.
Davis. Natalie.
She's in the bathroom.
Bathroom. Janet. I actually heard it. Georgia.
Here.
Isaiah. Is there. Thomas. You're up there. Let's see. Spencer. Parker.
Online.
Online. That's right.
That's all I'm like, it's everything else away.
Spencer Parker. There he is.
Here.
Caleb.
Here.
Carolyn.
Here.
Austin.
Here.
Morgan.
Here.
James. Bo.
Here.
Mercedes.
Hola.
Juan Carlos.
He's at home, I think.
Hey, good job saying hola there.
Is he, I didn't see him listed on mine. Damn it.
He wasn't here first period.
All right. So I got to do that, and then I got to do. That. And they should come up in just a second. All right, take out your notebooks. Take out your notebooks. We've been away 3 days. We've been away 3 days. Let's review a little bit. Make sure we didn't forget something. For your information. Next. CP, physics, test. I can't even spell test today. It's Friday, 9/11. That's this Friday. All right?
This Friday.
Yes, I will give you a study guide tomorrow, a physical paper study guide that you will have to write the answers on and turn in. Because last time y'all cheated, and you didn't even cheat good.
I didn't cheat.
I didn't.
You didn't even cheat good. You didn't even change the font on the thing. It was like,
What was it?
man, y'all can't even cheat good.
In class?
Quite a few.
In class?
I think there was a few in this class. I'm not really sure who did the actual work on it, because of course I can't tell whose is the original, but I got them turned in and I was like, dang, this one looks just like the other one that got turned in. The spelling error is even in the same place and it has the same picture on it. I wonder if that just one person did it and then everybody else said, hey, give me your... You don't even know how to cheat good.
Some people.
I'm telling you. All right. So open up your notebooks. Go back to Newton's first law. Go back to Newton's first law. Big Newton's first law. What was I getting? Change mask. Wearing me out. All right. So we're back to Newton's first law. All right. What is Newton's first law called?
Law of inertia.
Law of inertia. What does Newton's first law say?
Every object continuing in a state of rest for a uniform speed in a straight line has actually find unequal net.
Good. That would make, just say it, on a test, that would make an awesome fill in the blank question. Just say it. You know, that would make a really good fill-in-the-blank question. All right? Simply stated, what does Newton's first law tell us? Simply stated.
Objects at rest stay at rest, and objects in motion will stay in motion.
In a straight line,
At a constant speed.
at a constant speed, unless outside forces act on it. Okay? What is the definition of inertia?
Property of objects to resist motion.
Property of object to resist motion. Let's see. What is a force?
Any push or pull on an object.
Any push or pull on an object. What is the, you're not allowed to answer. What is net force?
Combination of all forces.
Combinations of all forces. You're not allowed to answer. Somebody else has to answer. How many forces do I have to have for something to be at equilibrium? Remember,
Equal amount of force.
two. I have to have a minimum of two. All right? Because if I've only got one force, let's see. What's the vector?
Any force in motion with both sides and direction.
Good. It has both sides and direction. What is a scalar?
It has only a size.
Only has the size or magnitude. What?
I don't know the answers right.
Matt, you don't know the answers.
Thank you. So much.
What are some examples of
You
scalars?
don't know. Yeah, I got it. Carolyn, your turn.
What?
An earthquake.
An earthquake? Yeah, I reckon it could be. But more simply, what are scalars? Scalars only have what?
Size.
Size. Therefore, what are my scalar quantities?
Weight.
Mass.
Grams.
What else? What else is always a scalar?
Carolyn's got it.
You lost me. You entirely lost me.
Should be in your notes.
It's not in the notes. You have lost me entirely. I'm not in there. Not part of our notes.
Scalars only have quantity. Mass.
So any kind of, any measurement.
Okay. So give me some.
So mass and
Tick, 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 tick.
length.
Length. Tick, tick, tick.
Time?
Force.
Time.
Oh.
Yeah. Took a minute.
But doesn't time have a direction? You can go
No.
forward and
Time, but it only has one direction. Therefore, it only moves. Time is always a scalar.
Because you physically can't go back.
And you physically can't go back.
Alright.
So time, mass, length, temperature.
Temperature can go down and up though.
That's true.
Temperature is a scalar.
But how?
Because it is a measurement of quantity, not of direction.
Oh, okay. Like when you're looking at it, you're asking
Yes.
for the number, not which way it's
I'm asking the number, not which way it's moving.
Alright.
Change in temperature,
Yes.
That's not.
delta. I can't remember, temperature is, can't remember what the sign for it is off the top of my head, it's not T. But anyway, delta temperature would be change in temperature, that would be a vector. Okay? Alright, what do we get when we add two vector quantities together? It's called a what?
Resultant.
A resultant. What are parallel forces? What are they on? The same what? Parallel forces.
Adjacent side.
Think about it.
Horizontal. How does
They may not always be horizontal.
Equilibrium?
They can create equilibrium, yes. But they're always going to be on the same what?
Is it a position guide?
Starts with a P.
Position.
No.
Parallelogram? I don't know. There's a lot of words on
No. They're parallel forces, so they're on the same what?
Plane.
Plane. Parallel forces are always on the same plane. Are they necessarily in the same direction?
No.
No. Okay, so if I have my box here, and I have two separate forces, each has 5 newtons, but they're separate forces. All right? How much force have I got to the right?
10.
10 newtons to the right. All right? If I've got 5 newtons to the right and 5 newtons to the left,
0.
0. See, I can just add them. And then if I get 5 more over here, now what's my net force?
15.
Nope.
5.
10. No.
5 minus 5 plus 5.
5.
I've got 5 newtons to the right. Okay? Got 5 newtons to the right. I can just, anytime forces are parallel, I can just add them.
Okay, so do you base which way it is, like right or left, based on which one, like the majority?
Yes.
Okay, look. So the reason I said 15 is because you said net force is the sum of all the forces. So when you say net force, do you mean sum of all the forces that are getting a response?
Yes.
Okay.
All right. And here and even though I drew a line over to the left, so obviously it's an opposite force. So if I drew this up here, right, and then I would draw my negative one here, and I would realize I have a net of 5 right here that's not accounted for.
Yes. So it's kind of like whichever way the number line goes. Like this way is negative, this way is positive.
Yes.
That makes sense. Okay.
Same thing here.
Yeah. That makes sense.
Okay? As long as they're parallel, right? If they're not parallel, right? Is that my next thing on here? They're not parallel. What if my forces are not parallel? How can I figure out my force vectors? All right, so remember my box? And my friend Bob is a jerk. All right, and I'm pushing with 3 newtons or 4 newtons here. He's pushing with 3 newtons here. All right. Can I just add them?
No.
No, it didn't work like that. What do I use?
Parallelogram.
All right, that's where I use my parallelogram rule. Parallel. Parallel. I never can spell good. Spelling is like, I never got past the first round of 2nd grade spelling bee. I can do math and science like a monster, but I can't spell.
I think that O is supposed to be an A. Parallelogram.
Yeah, might be. Anyways, parallelogram rule. All right, that's my parallelogram rule. All right, so now all I've got to do is what? Draw my force vectors. All right, I know I've got 3 newtons. We'll call that up. And I've got 4 newtons to the right. And then I draw my parallelogram. Right?
Yes.
Then I connect my 0 and where the 2 lines cross. Now I have the direction of my vector. Right? And now I use the what?
Pythagorean theorem.
Pythagorean theorem, which states?
A squared plus B squared equals
3 and 4 those are going to be 5.
Yep.
Okay.
And we always use our hypotenuse is going to be our C. Okay? It's always our C. So we know that this side is equal to this side. And it's going to be 16 plus 9 equals C squared. 25 equals C squared, square root of both sides. And we get 5 equals 6. So now I know that my force vector is 5 newtons in whatever direction we call that, to the side, okay? Whatever direction we decide to call that. At a 60-degree angle. All right, because we're going to have a 30, 60, 90 there. All right? We'll go with the parallelogram rule. Yes?
Sure.
All right. You can use the parallelogram rule to find out where the forces are greatest, right? Remember the gorilla hanging on the rope? Coach Anderson's pet gorilla, right? And there's my gorilla. Gorilla. All right, it's hanging down. Forces here. That force is there. I can figure out my parallelogram rule. I can use it here to figure out where my forces are the greatest. Okay? Yeah. All right? And obviously it's on this side, all right? Because it has the longest line on it. All right? All right. Let's not leave my gorilla hanging too long. What does this symbol mean? What does that symbol mean?
Sigma.
Sigma. Okay, that's my sigma.
It's the sum.
And that is sum. What does it mean when I sum things?
Put them together.
It means I add them up, put them together. Okay? What does this one mean?
Forces.
It means my forces. Right? So, if I have sigma F, that equals the sum of my forces. All right? And if I have sum forces equals 0, that means I have, if the sum of my forces is 0, what have I got? Yes, you said it. Equilibrium. All right, anytime I have some forces equaling 0, I've got equilibrium. Means I have no net force. All right, questions so far? Am I with me? All right. So we seem to be moving along fine. All right, let's see. What's another name for the support force? Yeah.
Gravity?
What?
Gravity?
Nope. Normal force. Okay? That's my normal force. All right? What is normal forces, my normal force or support forces relationship with the structure that is supporting, with our supporting structure? What is the normal force's relationship to the supporting structure? It's always what?
Against it?
Yep, what's the geometry term?
The
What's the normal force's relationship to the supporting force?
The supporting structure.
I said against it, he said, let's leave it on.
I can't.
Well, the like, I have something similar to what you said, but it's not what you said, so I don't know if this is right. But it says always perpendicular to the supporting object, but I don't know if that's
Correct. It is always perpendicular. So normal force is always perpendicular to whatever my supporting structure is. So, if my object is here, and my supporting structure is there, what direction does my normal force go in?
Down? Up?
No, down is what?
Gravity.
Gravity. Up is my...
normal.
It's going to be up. And if it went through, it would make a 90-degree angle. Okay? So I know if one's 90, they're all 90. All right? Now, what if I have an inclined plane? Where is my supporting force? What angle?
Down.
Now, down is always going to be what?
Like diagonal.
Yeah, it's going to be diagonal across the board.
Yeah, that's what I meant.
And through, so that I get 90 degrees. All right, it's always going to be perpendicular to the supporting force. All right, it's always going to be perpendicular. So if my gravity is greater than my normal force and force of friction, what's going to happen to the box? It's going to slide down the slope, right? All right? So our net sum of forces is now unequal. All right? Does that make sense? What produces normal force?
The Earth.
Nope. What's it called?
Gravity.
Chemistry term.
Van der Waals.
Van der Waals forces. All right, if I'm going along in a car and I'm sitting in the car, what is my equilibrium with? The car or the earth?
The car.
The car. All right. I may be changing speeds. I may be accelerating. All right. And when you hit the tree, you decelerate. Okay. So equilibrium has to do with what object you are in equilibrium with. We are in equilibrium with the gravitational field of the Earth. What do we call a change in position?
Motion.
Motion. That's motion. Very simply. How do we calculate average speed?
You do distance divided by time.
Distance divided by time. How do we get instantaneous speed?
Speedometer.
Use a speedometer. And remember, instantaneous speed means that we have, instantaneous means time equals none. It's infinitely small. So even with really great, difficult math problems, we can only get to a certain degree of accuracy with instantaneous speed. We get really close on some things and almost exactly on some things, but other things that are moving really fast or maybe might be changing directions, it's really difficult to get that instantaneous speed and make it be exactly right. Okay, let's do a little graphing exercise. And I want to do this because I need to start introducing y'all to physics graphs, which are a little, ever so slightly different. All right? And if you don't start doing them now and practicing them now, y'all will mess these up. All right? You're going to draw a lot of graphs. Now hear that? You're going to draw a lot of graphs. So let's start with the basics. Okay? Our basic time versus position. Graph. All right? First thing. Our position is our horizontal axis. Right? Our position is always going to be our horizontal axis. Time, God, I'm losing my mind. It's going to be on our vertical axis. What is wrong with me today? I slept good last night. Maybe that's what's wrong with me. Time is always going to be our horizontal axis. All right, so time is always going to go this way. Position is here. So this is going to be a little different from your math graphs, because when you do a graph in math, this is always X, right? This is always Y. All right? Your vertical graph is going to be your X position, your Y position, or possibly your displacement. All right? Or we can get displacement from it. Remember, S is displacement. All right? So we're always going to be, that's always going to be on our vertical axis. Time is always going to be our horizontal axis. What's missing?
The other side.
2 quadrants. We don't have any quadrants over here. Why not?
Because time can't be negative.
Time can be negative. Time can be negative. All right, we've yet to discover a way to go back in time. So time's always going to be positive. So we can just throw away these quadrants over here. All right?
Can't you, like, if you're doing time, can't you get rid of the bottom part, like, and stop it?
No, because your position can be negative.
Yeah, your position can be negative.
Oh, sorry, I mixed up. Sorry. Okay.
But we can do away with this because time goes this way.
Gotcha.
All right? Position goes here. All right? So you're always going to have position, time, nothing. All right? There'll be lots of nothingness. So this is gone. Okay? We can't do negative position. All right? Or sorry, negative time. All right. So let's plot a real simple one here. All right? We'll call this 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, and we'll call this 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and then we'll plot position time up here. All right, time, position. All right, we'll say we're at 0, 0, 1, 1, 2, 2, 3, 3, and then 4, 4. So if we plot that up here, 1, 1, 2, 2, 3, 3, 4, 4. All right, we can join those together. All right, and that's the, try to make a straight line here. All right, make a straight line. Now I've got my position time graph. I've got them all together. And I can learn a lot from this graph. All right? Okay, I can learn a lot from this graph. I can give it direction and displacement. Okay? I can figure out what my speed is. All right? My speed is always going to be my rise over my run, which means this, it is the same thing as distance divided by time. All right? That's always going to give me my speed. I can get my average speed, I can get instantaneous speed, all right, or an estimated instantaneous speed, okay, but I can get all of that from that graph at any point I want to along it, all right, so I can say if I want to find the average speed for the first 3 seconds, all right, so I go out to 3 seconds, I realize it has moved 3 meters, so 3 meters divided by 3 seconds equals 1 meter per second. All right? Now I know exactly how fast it's moving. It's moving 1 meter per second during that whole time right there, or 1 second. All right? 1 meter per second. So now I know what my speed is. All right? If I want to make it a vector, I have to give it a direction. All right, so I can say that this is to the north and this is to the south. All right, so north and south. So in this case, I have a vector moving 1 meter per second to the north. Now I have a velocity. All right, now I have a velocity. Pretty simple math problem. All right. But make sure we get all of everything that's where it's supposed to be first. So I'm going to give you a set of times and positions, and I want you to practice making a time versus position graph. All right? And I'll make it really simple. All right? Time, position. We're not going to name position yet. All right? So we're going to start at 0, 0. And these are in seconds. This is in meters. All right, so real quickly, just make a little graph with those values. Remember what you need and what you don't need. We're going to say that the meters are all positive. Okay? There are no negative values up there. All right, should be really simple. Everybody done?
Yeah.
All right. So what's the first thing I should do? Make my horizontal axis first, right? And that's going to represent, and that's going to represent
Your
position. And my position here is X, so I make it X. All right, make my origin point. From my origin, I go to the horizontal axis, which goes to the right. All right? Now, here's where you got to have a little intuitive sense. All right? When I make an initial graph with information on it, I want to use values that make the graph make sense. Now, really easy with seconds here. I can just divide my graph here into 4 seconds very easily. Now, since I've made them that big, do I want to make each meter that big?
No, every 5.
No, I don't want to do it like that. I would have a lie. It would make no sense. Okay? So I need to come in and I need to think about this. I need to make a reasonable amount. And I certainly don't want to make 20 lines on here. All right? So I'm going to come in here. I'm going to make these worth about 5 each. Okay? And looking at this, you can come up with a lot of things intuitively that I don't even have to think about. I kind of know what's going on here before I even graph it. But that's why I made it easy for a purpose. Okay? So at 1 second, 2, 3, 4, 1 second, I move 5 meters, right? 2 seconds, I've moved 10 meters. 3 seconds, I've moved 20 meters, or 15 meters. 4 seconds, I've moved 20 meters. I should have somewhat of a straight line between 0 and 20. All right, I can figure out my speed, right? It's my rise over my run. So I can take that from anywhere on here. I can take it as an average. We'll take it here and we'll do it from 20. All right, 20 meters. Took me 4 seconds. And that's going to divide out to 5 meters per second, right? Is that correct? Should be. I mean, it's pretty obvious. That makes a really easy graph. Makes a really easy graph, easy to do. Now, let me give you a second set of numbers to put in there. All right? Yeah, you two can go now. You can go. All right, so let me give you a second set of numbers. Let's do it on the same graph. All right? You too. Let's use that same graph. Did you need to go to the train? Now, I want to keep everything the same. I'm going to hurry up so I get this done before the announcements come on. So I want to keep my 5 meter consistent here, but I know I'm going to need some negative values. So I'll go ahead and, since I know I'm only going to need 1, I'll just make my -5 down there. All right. My first X position at 0 is at -2. All right. My second position at 1 second, I'm positive 2, so that's going to be somewhere right in here. All right. At my second, I'm positive 6. That's going to be about O right there. 3 seconds, I'm positive 10. All right, that's about right there. And at 4 seconds, I'm positive 12. All right, so about right there. Now, this graph's going to look a little different. All right, it's going to start out in a straight line. But then, over that last second, it kind of gets crooked, doesn't it? Yeah. All right, now I can get some different information. All right. What is my speed during the first 2 seconds? All right. During my first 2 seconds, I can come in here, okay, position final minus position initial equals my change in position equals my delta 14. And it goes from negative, let's see, minus -2. And at 2 seconds, I'm at 5, what did I say? 2 seconds. 1 second. 2 seconds, I'm at, what did I say? 6, okay? So 6 minus -2 equals 8 is my change in position, okay? Divide that by 2 seconds.
Hey, Vikings.
4 meters per second. Now, is that my average?
Prayers, come Holy Spirit. In the name of the Father, Son, and Holy Spirit, amen. Come, Holy Spirit, fill the hearts of thy faithful, and enkindle in them the fire of thy love. Send forth thy Spirit, and they shall be created, and thou shalt renew the face of the earth. Let us pray. O God, who didst instruct the hearts of the faithful by the light of the Holy Spirit, grant us in the same Spirit to be truly wise and ever rejoice in his consolation. Through Christ our Lord, amen. In the name of the Father, Son, and Holy Spirit, amen. Teachers, please release your seniors and seniors only.
Is it the same as my average? No. My average speed is going to be different. My average speed is actually going to work out to 3 meters per second. All right.
Teachers, please also release your Viking Hour students and seniors only at this time.